50, but let's get going. Okay, so thanks for joining, everyone. I know it's a Friday morning. I know for a lot of you it's been a long conference, and I know debugging is not necessarily the thing you want to jump into first thing in the morning, but I appreciate you joining us, and that's where we're going to start. So a few introductions to begin. So my name is Steve Abbott. You're going to be hearing from me first. Trey White is going to be presenting second towards the latter half of the talk or the tutorial. Kostas Makrides is going to be our silent partner here in terms of not presenting today, but he'll be in and around in the chat and answering questions as well. So the three of us are all members. If you don't know us already, we're members of HPE's Coral 2 Centers of Excellence. So working our way backwards, just some short introductions. Trey White is the technical lead for the Frontier Center of Excellence. So he's recently been promoted into that role from just kind of being an applications person. So whatever room you're sitting in with whatever coffee you have, go ahead and say, good job, Trey. Congratulations on the promotion and the extra work that you now have to do. And I'm sure Trey will feel those good vibes out in California. Kostas is on the El Capitan Center of Excellence side. So he's works at Livermore, works closely with all those application teams on helping them prepare for El Capitan, and actually all the TriLabs application teams preparing for El Capitan. And I'm Steve Abbott. I'm a little bit different from Kostas and Trey in two different ways. First of all, I'm a joint member of the two centers of excellence. So that means I get it coming and going. And then the other way that I'm a little bit different is where they're both applications people and come out of our benchmarking and applications teams. I'm in our Cray Programming Environments team. So that means that I sit on a special team inside Cray PE called the Performance Engineering team, where we're really kind of an internal group of users. We take your applications, we run them with our tools. We try and make sure that our tools are working correctly on them and try and understand how your applications are working, the sorts of things that you're trying to do to make sure that we can really do the best that we can. So you'll talk to me a lot in the course of the Center of Excellence work, but often you'll talk to me when things go wrong and not necessarily when things are going right. So I'm also part of what I do is I help if you run into an issue with Cray PE, like a compiler issue or an MPI issue or something like that. When we take it internally and try and work it out, I'll probably help out. If I know your application, I can better help our team understand where your application went wrong. Okay, so that's just a way of introduction. And so we've been working, preparing for Frontier and El Capitan for several years now, and we've developed sort of some background knowledge and some useful techniques when it comes to debugging on these platforms and doing some profiling on these platforms. And we thought it would be a good opportunity to share that since we're getting pretty close and many of you are already working on early access hardware. So I'm going to take this first section. Like I said, here's a rough flow of what our morning is going to look like. For the first probably hour and a half to hour and 45 minutes, you're going to be listening to me talk to you about debugging. Debugging is sort of a difficult thing to teach. So what this talk is really going to end up being is a lot more of an introduction to how I go about debugging and how I think about finding bugs and some tools and tricks that we provide and that we've discovered to help you come at your bug and figure out what you're working on. So we're going to start by talking about what kinds of bugs you could possibly have, because in my philosophy of debugging, understanding the possibility space is a really big part of understanding where your bug is and how to get to it. So we're going to start by talking about that possibility space in the section I call entomology. And then we're going to kind of dig in and run through a gamut. I'm going to show you a bunch of different tools that you can use to find your bug. I'll try and talk about how those tools can be used, and the different types of bugs that they might be useful in finding and why you might pick one tool over a different tool. And then we're going to open up the fire hose and we're going to look at using some runtime logging. So both our HPE's open MP and OpenACC offloading runtimes have a lot of really useful debugging or logging information that you can get out that can be helpful in understanding how you can find bugs. And also AMD's runtimes, both their HIP and HSA runtimes, and also their OpenMP runtimes present a lot of that information as well. And so we'll talk about how some strategies that you can use using that runtime debugging information. And then towards the very end, we're going to talk about active debugging. Now, I think there's a good chance that many of you came into this talk expecting we would mostly be spending it in a debugger. And actually, we're really only going to touch on debugging in a debugger at the end. And I'll try and give you some strategies for using a debugger. You know, one of the really tricky things about using GDB or GDB for HPC or rocgdb, or even the graphical debugging tools, is that really when you need them, you don't want to learn them, right? If you're trying to find another bug and you fire up a debugger, you have a hard time learning to use the debugger at that point. And so I want to give you some tips and tricks that make that transition a little bit easier and maybe will help you get over that hump a little bit easier. And then once you really learn a debugger, it becomes much more of a go-to tool. But we're going to talk about that mostly at the end. We're going to talk about more strategies and approaches to begin. And then in the second part of this talk, picking up after the 2-hour mark, we'll take a break between part 1 and part 2. Trey is going to pick up and he'll walk through some profiling stuff with you. So I'll let him introduce his talk when he gets there. Okay, so throughout the course of this talk, we're going to reference an application, in one application in particular, and this is just because we thought it would help to concretize what we're talking about if we're always talking about the same application. And so the application that we're going to use here is Faces, which is a spectral element micro benchmark that Trey put together. So Faces is a 3D grid of spectral elements. So here's a visualization of what that might look like, where we have one of these spectral elements that's laid out on this grid. Those spectral elements share some number of faces that have to be summed together. And those faces are partitioned across MPI ranks. And then those MPI ranks are set up in such a way, or the micro benchmark is written in such a way that it can exchange contiguous buffers for MPI. So one of the reasons why we're using Faces for this, even though it is a micro benchmark, it's relatively small. For both profiling and debugging, there are some disadvantages to using something small, especially because it sometimes makes things look a little bit easier than they are. But Faces actually has a lot going on with it that makes it amenable to us showing off a lot of different things. So it has both a CPU version of this exchange as a reference implementation, but Trey has also really used this as a test bed for iterating on GPU-aware MPI, on the Frontier platform, and on the early access systems leading up to that, and also on NVIDIA-based systems. And so it's a tool for iterating on GPU-aware MPI, on asynchrony, on different communication strategies. And so it's a useful tool in that we can introduce lots of different kinds of bugs. Okay. So I'm going to dive in and we're going to kind of talk about debugging strategies. So I'm generally not going to be watching the chat throughout this just because it would be a bit distracting for me. Both Trey and Kostas are in the chat, so hopefully they can answer any questions that come up. I'll stop every once in a while, check through the chat, see if there's anything that hasn't been addressed, and I'll try and answer any questions and address it then. Okay. All right, so let's talk about debugging. And let's talk about my strategy of debugging. And I'm going to, as I go through this, I'm going to expect that for a lot of you, you'll be hearing some repeated material, but you'll probably, hopefully also be hearing some new stuff. So I'm going to really start from the beginning and try and build a good foundation of how I approach debugging and what we can look for in bugs. And as we build that up, hopefully you'll learn something, or at the very least, it'll reframe things in a way that might be useful to you. So the first place I start whenever I encounter what I believe is a bug in code is I ask myself, what kind of bug is that, right? So really, in my mind, there are 3 major types of bugs that we run across. There's always going to be edge cases. There's always going to be weird things, but they really come in 3 flavors. Either your code crashes, it hangs, or it gives wrong answers because of a race condition somewhere, right? There's, of course, another answer here which is that you just, wrote something wrong and you're getting the wrong answer. That's actually, I guess, now that I think about it, not the kind of bug that we're going to talk about here, just because those can be so specific to your method, typos and coding issues and all of that. Some of these tools can be leveraged for that as well. But for the purposes of this talk and the purposes of the tools, we're really just going to look at bugs that are apparent or that fall into these three categories. So in a crashing bug, one or more of the processes in your application terminates. I think overall, the type of bug that people come to us for help with the most is a crashing bug. And generally, it's also the easiest kind to solve. Now, there may be some self-selection there, right? A crashing bug is much more obvious when it happens. And so it's the one that we probably see the most because it's the one that people notice most quickly. But it's one that will spend some amount of time understanding the different ways your application can crash and how you can deal with it. Hangs are a little bit less common, but they do occur pretty frequently, especially in parallel applications. And I'm going to categorize hangs into two different types. You have deadlocks and you have live locks. So what's the difference? So a deadlock is when your application is executing and all of your parallel actors are stuck waiting for something that never happens, right? Everybody is in the same place, or everybody just kind of reaches a point and stops there and sits there spinning, waiting for something to happen. So a good example of a deadlock is, maybe everybody arrives at an MPI barrier except for one process who is often never land spinning on a while loop, right? And I would consider that a deadlock then. The state of the application is fixed and we're just sitting there waiting for something that never happens. And that's relatively easy to see in a lot of circumstances. A live lock is a little bit trickier. In live locks, everyone is playing kind of hot potato, right? So they're progressing from a thread level perspective. We see them moving forward and executing. They're burning cycles. They're printing output, but you're not actually making any progress. And really what's happening in this case is that you're passing back and forth something that needs to happen. The threads are trading back and forth in a small scale progress, but not actually making any global progress. And we'll consider that a live lock. So, trading a mutex back and forth might be an example of this, or an application that is waiting for some threshold set of particles to be processed, and everybody thinks that somebody else is supposed to be processing those particles when really the particles are exhausted, right? We would consider that a live lock. And then race conditions are a little trickier to diagnose and a little bit of a, let's say, redundant for some of these, right? So you may see crashes that ultimately are from race conditions. But the core idea of a race condition is that one or more actors in your application are trying to access the same data at the same time, and they're doing it in a way that's not deterministic, right? So this can show up as if you have multiple threads that are trying to write to a memory location, and they clobber each other and give you nonsense results, or they overwrite each other. That's a good example. That's a common case where we see this. And so that might show up as results that you run your application once and it's correct, and you run it a second time and it's incorrect. Sometimes race conditions can result in crashes where you have data that's being raced to, that things are clobbering each other, and you get nonsense numbers that then lead to a crash. But often it's just wrong answers. Now, when I've been kind of careful here to say actors in your application, so race conditions aren't just between CPU threads, which is, I think, where we often think of them. Now that we have GPUs in contention, we can be talking about a race condition between different GPU threads, or even between the GPU and the CPU, right? So in this characterization, broad synchronization problems where maybe you're copying data off of the GPU while a GPU kernel is still running, I consider those race conditions as well, because that really, they fall into that category. So this is the three major types that I tend to categorize things as. So let's dig in a little bit more into those types and the details that come from them. This section of the talk could also be called words mean things, or listen to what your application tells you when it crashes. So on the CPU world, we're pretty familiar already with crashing bugs. There are things that we see a lot, and the most common of these is probably the seg fault, right? It's so common that I will often have people come to me and say, my program is seg faulting, when it's actually just crashing with a different error message, right? So when a bug crashes or when an application crashes on the CPU, it's going to emit a signal. So there's a man page here that you can check if you want to know more about signals or more about the details of signals. And that's man 7 signal. So you can do that on any, should be almost any machine in our machines for certain. And that's going to give you a cheat sheet of signal names and the numbers, right? So when your application fails, it's going to give you one of these, and paying attention to the details of what that signal is and how the application crashed and what the kernel tells you about the application crash can actually be really instructive and give you a lot of insight into what your bug is. So the most common of these, like I said, is a segmentation fault. It's also called a SIG-SEG-V or a SEG-V. And that's going to be a signal number 11 if you're going to bother checking that number. And this has a pretty specific meaning, even though it sometimes feels like a generic error. And what it means is that you attempted to access memory that exists, that could be accessed, but is outside the virtual address space the kernel gave you. So what do I mean like that? Well, let's take a step back and look at kind of a simplified memory model of the Linux kernel, or how your application runs on the kernel. For somebody that is really into systems work, this is going to be oversimplification and wrong, but it's a useful mental model for you to keep in mind. Your application starts up and you make a call like a malloc, right? And that malloc, you tell or effectively telling the operating system, I would like this chunk of memory, right? If you say malloc 1024, I would like 1024 bytes. And the operating system looks at the available memory on the system and it says, okay, I see a section of physical memory that is currently not assigned to anybody, and there is enough space there to fit the 1024 bytes that you've requested. So I am going to carve out that section of memory as belonging to you, and I am going to give you a set of addresses that you can use to access that memory. Now those addresses are not the same addresses as the physical addresses of the memory. The kernel maintains a structure called a page table that it keeps track of the addresses that it has given to your process and how your process can access the memory and where that memory maps to in the physical hardware. And so this is what lets us do things like migrate memory, right? Either migrate memory between NUMA domains on a CPU or migrate memory between the GPU and the CPU. Your application just gets a single virtual address, and the kernel or the GPU device driver underneath that maintains that page table that maps from that virtual address to the physical address. So what a seg fault means is that your application attempted to access an address, and that address was outside of the virtual address range that the kernel gave you. Now, that address could map to an actual physical location on the host or in the physical memory, but the kernel didn't give you permission to access it. And so the kernel says, no, you have violated what I've given you, and it throws it gives you a seg fault. All right. So this tells you that you've indexed something, or you're attempting to access memory that is probably not very far away from the actual application memory space that you're allowed to have. It's just you've gone a little bit too far beyond it. And so this generally means some sort of indexing error, or maybe a pointer that's assigned a little bit wrong. Right? These are the most common cases, or maybe you forgot to, or you freed memory and tried to access it again. These are the sorts of things that generally call a seg fault. So seg fault sort of says you stepped out of bounds, but within the local neighborhood of where your application is supposed to be. This is in contrast to a bus error. A bus error is you attempted to access memory that cannot possibly be accessed on the system. Right. So whereas a seg fault was you stepped a little bit outside into your local neighborhood, the address could potentially exist on the system. A bus error means you tried to access a memory address that is so wild, there is no way the kernel could have possibly given you that memory address for your application to use. So a good example of sometimes where we'll see this is if you have an indexing error that comes from an integer overflow, right? As the size of memory on the system has increased, we see people starting to switch between using 32-bit integers for indexing versus using 64-bit integers for indexing. And if you incorrectly cast from a 64-bit integer to a 32-bit integer, you can get an integer overflow that reads as a massive, massive address that's way outside of the bounds of what you could possibly read that could possibly exist on the system. And in those cases, it'll throw a bus error. Now, you'll also sometimes see bus errors show up in driver issues, but that's at a level where if you hit one of those and you're relatively certain it's not your application causing it, then we have other issues that we need to sort out, right? And you'll come to somebody like me, or you'll open your ticket with your site and they'll work that through. But your application can hit bus errors. They're just a little more rare in CPU side applications. And then the third type of crash that we see really commonly is an abort. And an abort is normally, in my experience, a good sign, right? So this means that your application or a library that your application uses realizes that something was going wrong and intentionally stopped execution. It intentionally bailed out. And a good example of this is if you have an assert statement in your code that says, this variable must be less than this value. When that assert trips, if something has gone wrong earlier in your execution and that assert trips, you'll get an abort. Right. So it's not a good sign in that something is wrong with your application, but it is a good sign in that something is wrong with your application enough that you have at least noticed that it's going wrong before it gives you wrong results, right? And hopefully, if you're writing your code with good asserts in it, this is going to occur somewhere in the neighborhood of where your issue actually is. The last type of crashing bug that we'll talk about, and again, there are some other types that are just far less common, is a floating point exception. So a floating point exception means that you try to do some dangerous floating point math, something that maybe yields an infinity or a nan, or gives you a denormal, right? A number that's really, really close to zero. And you ask to be notified about it. Now, some compilers, I think some versions of LLVM and maybe the Intel compiler will default to floating point exceptions on, but most compilers will default to having floating point exceptions off. They'll let you do that dangerous floating point math. So this is something that there's some registers that need to have some bits flipped on the processor, so that the processor will raise an exception when it detects this floating point, these dangerous floating point operations. So as a general rule, I'll say, I think most of the time when I see floating point exceptions, where they're occurring is somebody is getting a nan in their code, right, and not a number value out of an output. And they decided to enable floating point exception trapping or floating point trapping to try and find out where that nan is originating from. Right. And if you're lucky, when you turn on floating point exceptions and you raise the SIG FPE, it's going to happen right at the place where that nan was generated, and you'll be immediately able to work back from that. In general, I'm going to say that most of the time when I go to try and debug something by turning on floating point exception trapping in the compiler, I hit probably 4 or 5 nans that occur before the one we actually care about, because you are probably dividing by 0 more often than you realize in your code. You're just never actually using those values for anything. And this doesn't discriminate whether the value gets used afterwards or not. Okay, so this is the common family of crashing bugs on the CPU. Let's take a look at when we move on to an AMD GPU, what those same crashing bugs translate into. Because AMD has done a lot of work in their runtime to try and map errors on the GPU to analogous bugs on the CPU. And so when you do an access on the GPU that fits broadly into one of these categories of these signals, the runtime and the kernel and the device will raise, or the device will raise an exception, and it'll say, hey, something went wrong here for me, and it will translate that down, and the runtime on the CPU will catch that and translate it into an appropriate signal and cause your application to fail with the correct signal. All right, so here's the mapping. And I've put here on the right-hand side the types of message that you'll see out of the AMD GPU runtime. And then on the left-hand side, on the right-hand side, I've put the signals that those map to. So when we see this memory access fault by GPU nodes, whatever, or an agent handle, that maps into a seg fault, right? That means the same thing as a seg fault, that you tried to access memory on the GPU that it potentially could access, but is not allowed to access. All right, and this particular flavor of a memory error is really nice because it gives you, as part of the printing, it gives you 2 pieces of information. It gives you the address that the fault happened on, and that address can be really instructive. Especially if you're going to take that information and then go into a debugger and inspect memory addresses, this can give you an idea of the neighborhood within your application where that fault may have happened. And it also gives you a reason code. Now, the thing that you need to be a little bit careful about. So right now, in this case, we got a very instructive reason code in this demo example, which is we got reason, page not present, or supervisor privileges. So this is instructive because it tells us that, again, we tried to access memory that we potentially could access, but it was outside the bounds of what we were allowed to access. So that's kind of what that supervisor privilege part of this means, right? Is that if I had root access and could touch any memory that I wanted on the system, or if I was running a process that was allowed to be that wild, then I'd probably be okay, but I tried to touch something that I didn't have permission to touch. Now, something to remember is when we're running a full frontier node at full capacity, we're running, a full crusher node at full capacity. We're running a 64-core CPU with 2 hyperthreads, and we're running 4 GPUs, each with 2 GCDs, each of those possibly with thousands and thousands and thousands of threads. So there is a lot going on running on the GPU or running on a system, and there is just one kernel. So when we hit a fault on the device, sometimes this reason code doesn't get populated well. Right, and that's just because sometimes there's just so much going on, and all of this is happening in a split second, and the kernel tries to catch the information, the device driver tries to catch the information, and sometimes it can't. And so this reason code may sometimes show up as unknown. And when that happens, it's unfortunate, but you still have the memory access and you still have the meaning of the signal to trace back from, right? There's another flavor that this comes in, and when, the question is when we get this memory access fault by GPU node 5 versus this HSA error memory fault. It's a little hard to determine. Sometimes we see one, sometimes we see the other. Different runtime environment settings with the same bug can cause one error or the other. So it's just something to be aware of, that they essentially mean the same thing. So if you're not aware, their HSA is the heterogeneous system architecture layer. That's a layer that is kind of really the core base layer that AMD's runtime runs on top of, and a lot of that information. So these HSA errors are coming from being handled from a lower level of the runtime, but they still are GPU information for the most part. Technically, they could be CPU information, but we really mostly see them just for GPU errors. And all of these HSA errors, these last three down the side, if you look at the bottom here, you can see there's this detailed kind of information about which runtime source file the error came from and how many milliseconds we are, and this device callback queue information. All of that is going to be prefaced in front of what I have in the chart here. And that's, again, because we're bubbling up from such a low level. All right. And this means, again, the same thing as a seg fault. This HSA status memory error fault, you try to access memory that this is, I guess, is a slightly different flavor. The GPU can't access that memory, right? It's there. You could potentially get to it through some means, but the GPU and your kernel running on the GPU doesn't have permission to access it, is not able to access it. Okay, so these are, again, just like seg faults are the most common type of crash we see on the CPU. This is going to be the most common type of crash we see on the GPU. And then there's also a bus error analogy to on the AMD GPU runtime, and that's this HSA status memory error, error memory aperture violation. So this one is actually great and instructive, right? Because it tells you right out the gate exactly what it is. You made a memory aperture violation. So this is if you try to access an address that is so far outside of what the GPU can access that there is no way it could have possibly accessed that, right? That must be completely and utterly wrong. And again, we see this with, for example, integer overflows is a pretty common way to see this. And then there's if we trigger an abort on the device, which is something that we can do, we have an assert, or rather than a printing assert, just a call an abort on the device. That'll show up as this HSA status error exception. And that'll show, then again, the AMD GPU runtime will match that to a SIG abort. So from the perspective of the kernel, or from the perspective of your CPU code, it's going to look like you failed with an abort. And that's going to come out of a place on the device where, again, either your code or some library code that you're using realized that something was wrong during the execution of a kernel and bailed out. Right. So this is the rundown of crashing bugs. And again, we spent a large time here. But I think it's important to really dig in and try and understand the difference between finding your bug and not finding your bug, or understanding your bug and not understanding your bug, could come down to understanding the difference between a seg fault and a bus error, right? And it gives you an idea of how far out of bounds you might actually be running into. So I'm going to just quickly scan through the chat here. I see some specific error questions. Unless Kostas or Trey speak up right now with anything that I should address at the moment, I'm going to push on.
Can you hear me? There is one that I answered partially, but I thought you might have a better take on, and that is, let me find it. How do you know if an invalid memory access is caused by users or by the compiler?
Yeah, that's a really, really good question, and not one that I have a very good answer to, because we do see that show up, right? It's always a little hard for me to tell just how often people are encountering compiler errors. As new as these systems are, and as new as the software stack is, it's probably more frequently than any of us would like. It's the one way that you can tell, probably the best way to tell, is to tune the optimization flags on your compiler. If you drop down to 0 and you're still seeing the memory access fault, it is, or still seeing a crash at runtime, it is more likely that it's your code's fault, but not necessarily your code's fault. If it works, another really good test is if it works with one compiler but not another. That's a pretty good indication. I think my advice in general is, if you crash and kind of run through these steps and you reach a point where you know where the bug is happening, or you know roughly what area of the code is crashing, and you do not believe that it's your fault, like you feel like you've made a good effort and are reasonably confident that your code is correct and believe that it's a compiler issue, then the best thing that you can do is submit a ticket to your site, and then they can get a ticket to whoever provided the compiler, right? Whether it's us or AMD or another vendor. And then you'll have somebody like me come in who has a lot more tools at their disposal to understand whether or not something is a compiler error. I have a lot of tricks that I can kind of pull out, and a lot of them are pretty far outside the scope of this talk in terms of looking at different kinds of output and understanding how things work. So I really think the best answer to that question that I can give is if you use some of the other techniques here and get to the area of code that you think is causing the problem, or where you think the crash is happening, and you feel pretty confident, or you feel like you've at least done the legwork to rule out it being an application error, that you should go ahead and just open a ticket and get somebody involved who's has a lot more experience looking at compiler bugs and can make that distinction. And honestly, if you open a ticket, and it makes it to us on, for example, the Cray compiler, or even on the AMD compiler, the first thing that I'm going to do is I'm going to try different compiler versions, because often a compiler bug is going to show up in different compiler versions, or show up differently in different compiler versions. I know that's not a very satisfactory answer. If I had a really good, clean answer to how to determine if something is a application bug or a compiler bug, I also wouldn't have a job. So it's a complicated topic, but a very good question. Okay. All right, so we're gonna push on to the tools, or we're actually not done with bug classification, but we're done with the really slow detail bug classification. We're going to accelerate as we go through. So there's another class of bugs that I'm actually not going to explicitly consider bugs here, or another class of failures that you can get, and that's MPI errors. So debugging MPI bugs could be really another talk. So I just want to point out a few things. So one of those things is that in most cases, when MPI detects an error, whether it's an internal error or some error that is happening within the application's use of MPI or within MPI itself, it's going to invoke its own error handler and use that and crash, right? And for the most part, when we're talking about MPI and we look at the types of crashes that can come out of MPI usage, our MPI implementation, at least, and this isn't true of all of them, but our MPI implementation mostly doesn't care for the buffers or GPUs or CPUs, right? Because the MPI processes at this time, the parts of MPI that are doing those transfers are almost all executing on the CPU. And so if you do an out of bounds memory access on GPU where MPI, and that falls out of bounds, right? You give MPI a buffer to copy, and you specify too long of a length, and it runs off of the end of the GPU buffer that you've hip mallocked. MPI is probably going to throw that as a CPU-like crashing signal, because the failure mode of the crashing bugs and who detects that the failure has happened is determined by who is doing the accessing, not where the access is. Right. So especially in a tightly coupled system like Crusher or Frontier, where the memory space is equally accessible by the CPU or the GPU, it really is important who is doing the accessing or what processor is doing the accessing, not where the access is. And the other thing that I really want to emphasize, because it's something that people very frequently forget, is that MPI returns an error code, right? Every MPI call has an integer error code that it returns. If it's in C and C++, it's returning as the value of the function. And if it's in Fortran, it's that I error integer value that's the last argument to an MPI call that the compiler makes you put in, and the overwhelming majority of people ignore. And why do the overwhelming majority of people ignore them, it's because MPIs, for the most part, default to aborting on error. So when they detect an error, they will crash and they will print out an error message about why they crashed, and then they'll give you a backtrace. But it's important to remember MPI calls do return error codes, and they return instructive error codes. And they're all over the place, right? All of those MPI wait calls where you pass in MPI status ignore, you could be passing in a status array and actually check the contents of that status array and actually see what sort of information comes out of it. So if you run into a case where you have a complicated MPI error, go ahead and check those error codes. And you can, in our runtime in the Cray mpitch, you can set mpitch abort on error equal to 0. And that will prevent MPI from aborting on error. So you can write your own error handling, right? You can check those error codes. You can print them out on different ranks and kind of really understand what's going on. Okay. All right, and then I'm going to briefly address, we already talked about this a little bit, but just a word on Heisenbugs. So a Heisenbug is a term that we all know and feel that we're a little bit clever every time we say it. It's a bug that disappears when you go looking for it, right? So the important thing to think about when it comes to Heisenbugs is they're not a class of bug by themselves, right? They're another type of bug, but when you go looking for it, it moves. So why do bugs move around? Well, there's a variety of reasons, but the core issue is that as you go hunting for a bug, whether it's by rebuilding with a different optimization level or running in a debugger or inserting print statements, as you do that, you are changing the memory map and the execution space of your application and the way that your application executes. So if you have a segfault and insert a printf, it may send the compiler down a different optimization route that's going to pad memory a little bit differently so that your bug, instead of crashing, may land benignly in incorrect memory, right? The bug is still there. It just may change the type of message or the type of crash that you get. So in all of these cases, I really encourage you to think about what the fact that the bug is moving is telling you, right? So for a really good example of this is if I have a race condition and I run in a debugger, that debugger may add some additional synchronization and my race condition will not manifest. And so think about the parts of code that you're changing or the parts of code that you're setting breakpoints in and how those breakpoints might be affecting where the synchronization is and affecting your race condition, and work backwards from there, right? I can't give you really generic advice here because you know your code a lot more than I do, but there may be a lot of really useful information. Okay, so we are at this point about, pretty deep in, about halfway into the talk, give or take, and we're just now getting to the tools. That really is by design. I really want you to think very carefully whenever you approach a bug, or whenever you see a bug in your code. I don't want you to immediately reach for these tools. I want you to stop and think about what kind of bug it is, or what types of error messages you're getting, and what the possibility space of your bug could be. And then you can start to break out the tools, right? Because reaching for a hammer when you really need a screwdriver isn't really going to do you any good. Okay. All right. There is a step 0 to debugging, and I've already alluded to it. Check your error codes. So if you're using a library and the authors of that library went to the trouble of returning error codes, you should check them. So here's a drop-in macro that I use for HIP that you could also use, right? Every single HIP call returns an error code. And also every CUDA call returns an error code. This is a drop-in macro that you can use that prints these really nice error messages. It tells you what file the error occurred in, what file the non-success occurred in, what line, and it prints the call that made it. Like, this is the exact function call that was passed to this. and it tells you the error that was returned both with the numeric code and with the name, right? Check error codes. If you come to me and say, hey, I need help debugging a problem, and you're using a library, and that library provides return codes or provides error checking, and you're not checking those errors, the first thing I'm going to do is go through and insert an error check around every single call that can take one. This is step 0. Check your error codes. Okay, now let's dig into the different types of bugs and the different types of techniques that we can use for finding out, working back from the point of failure to try and understand why it's failing. So any of those crashing signals or any of those crashing bugs that we looked at, almost all of them are going to drop a core file that contains the output of your process's memory space at the point of failure. So you can see which signals will drop core files. If you go to that man page, that man signal 7, take a look. And if it says core in the action that's taken, that means it's going to drop a core file. One thing that you need to be aware of is that the core files are bound by the ulimit command, right? So you need to make sure that your ulimit allows you is large enough, or your core file limit is a user limit is large enough to dump the core file that you want dumped. So here's an example using the Faces application running on an MI250X, where I've introduced a synthetic bug that causes a segmentation fault on 2 cores. And you can see the output of Slurm here is telling me I had 2 tasks fail, task 1 and task 0, and task 0 dropped a core. It seg faulted and it had its core dumped. And the size of that core dump is the size, again, of the memory space of the process that dropped it. So in this case, the size of that core file is 137 megs. All right. And so how do we use a core file? So the way that we use a core file is we'll just throw it into a debugger. All right, so here we can take GDB, just a base debugger. We give it the application that generated the core file, because the core file contains the full memory space of the process, but it doesn't contain all of the executable code and all of the debugging and source information. So we take that memory space and we pass as another argument to GDB the name of the application we want to debug, and we can load that core file in. And then we can see GDB loads up, and it loads the application and the memory space, and we can do some post-mortem analysis, right? So I can do a backtrace here, and this backtrace tells me where the crash happened, or where the signal, or excuse me, where the memory access occurred. In this case, this is Mugs. So Mugs is the CPU implementation of Faces inside the benchmark. And I can pull that up. I can do a backtrace. I can see where I faulted. I can do L for line to print the source lines. And I can see, oh, somebody introduced a +10 onto the state vector access here that is causing an out of bounds memory access. That was kind of silly, right? And in the case of the CPU, we get really the full application memory state, which in this case, this also will tell me I can print this state vector U. I can see what it is. I could see that it is this array class that is or array class is templated onto doubles and with 6 elements, or just maybe dimensions. I forget. Yeah, dimensions. And we can see the sizes of each of those dimensions. We can see the strides of those dimensions, and we can see the memory address where the values of the memory is stored. And so here, again, it's easy to see, all right, the variable J that we use to index the last dimension here is 2, or sorry, it has the value of 4. 4 plus 10 is 14. The upper bound of that dimension based on our class is 13. And so that's why we seg faulted there, as we had an out of bounds memory access. Okay. And there are some limitations. There's some issues with core files, unfortunately. And one of them is, let's see what happens if I try and load a core file from a GPU crash. So here again, I'm running a benchmark in the same configuration, but I've introduced a bug in a different place. And the place where it faults this time gives me an HSA status error memory fault, okay, where I tried to access an inaccessible address. And I do the same thing that I did before. Again, I get a core dump off of rank 1. So I go into rocgdb, I say rocgdb, here's my application faces, here's my core file core. Let's see what you got. But here I do a backtrace, and what do I get? Well, I get the backtrace is showing me the stack inside the AMD ROCm runtime where the abort or where the signal was raised. Right. And so, and if I go and look at the thread state, we'll get to this a little bit later on, but AMD GPUs are represented as threads inside rocgdb. If I go to look at the thread state, I don't have any GPU thread state here. Right. And so when we're debugging a GPU fault from a core file at this time, with this version of ROCm that I'm using to demonstrate this, the AMD GPU memory state is not part of the core dump. This would be a slightly different scenario for those of you that are running on NVIDIA GPUs instead. Right now, NVIDIA does have 2 methods to generate core files from NVIDIA GPU memory or in NVIDIA applications. They have a standard core dump that dumps the entire GPU application space, and they also have what's called a lightweight core dump. And a lightweight core dump will dump the execution state, so you'll get a backtrace in the kernel state, but you won't get detailed register or memory information. But right now, that, just as a side note for those of you on NVIDIA GPUs, but for AMD GPUs, we don't currently have that. I have no idea how this works on Intel, so maybe that'll be something for a future talk once we have a chance to play with those a little bit more. So that's one of the limitations, right? So we have a few limitations that come from core dumps. The first limitation of a core dump, of using a core dump for post-mortem analysis, is that each core takes up the amount of memory that the CPU process was occupying at the point that it dumped core. All right, so for this simple case where we only had 137 megabytes worth of RAM occupied, that's not such a big deal. But if you're working on a crusher node where you have 256 gigabytes of DDR, that's going to be a really big core dump, right? It's almost certainly going to blow out your home quota, and it's going to blow way past, even a lot of if you're doing a parallel job, it's going to easily blow out a lot of file systems. And then depending on the system and the system configuration and the settings that your administrator has set up, when your multi-process job fails, a multi-process job will either dump one core file, which is what happened in the case that I just demoed, or it might dump one core file for every failing process. And that's going to take up a lot of space and is going to be really, really slow, right? Because all of this has to happen at the time of failure while your application state is still there, and it has to all be written to disk, and that's going to be really punishing. And then there's the limitation that we just showed, which is that it doesn't contain the AMD GPU memory state at this time. And then again, core files are just post-mortem. So there are some limitations to core files. They're a really useful tool. They, for simpler applications and smaller cases, they're always a good place to start, is pull in that core file, take a look, see maybe the information from the core file gave you what you needed. But they aren't perfect, right? So one of the tools, and I'll stop for questions after we talk about this tool, one of the tools that can help and alleviate or mitigate some of the issues with core files is ATP. So ATP is the abnormal termination processing. So ATP is useful for crashes. Anytime that you're going to dump a core or your application exits or aborts, ATP can help. And sometimes ATP can be used for hangs. We're going to have some better tools that we'll talk about in just a few minutes about hangs that are better for hangs. But ATP can also be used if your application is hung. You can send it a signal through your batch system or through your scheduling system and send it a signal causing it to terminate, and ATP can pick up and handle that. So ATP on most systems with Cray PE, you can, or most Cray systems, you can just module load ATP. ATP needs to inject its own signal handler. So you'll either need to rebuild your application or relink against libATP sig handler. So if you are running with, or if you're building using the Cray PE compiler drivers, that's the capital CC, the little cc, and the FTN, when you module load ATP, will automatically insert the links to libATP sig handler for you. If you're not running, or if you're not using our drivers, you'll probably need to add those links yourself. But there's another rub here that's a little bit tricky, that this actually, as much as I wish to say that this would work on Crusher right now, I think we actually have an issue that's preventing this, that we're busy working through, which is that the workload manager needs to be configured by the administrators to invoke ATP. Right, so there is, in the case of Slurm, there's a Slurm plugin that needs to be added by the administrators. There's instructions on the ATP man page on how to do that, so that when Slurm detects the application failure, it has the ability, or knows that it can pull in ATP and pull ATP up and make it work. So there's an open issue I think we're working through with Oak Ridge we need to reconfigure our ATP build a little bit to make it sure it works with their Slurm. So I know that's being worked through right now. But let's talk a little bit about what ATP does. So in this case, here's me invoking a crash with faces using ATP. So I'm going to run through what's on my command line here. I'm setting this HSA XNAC flag to 1. This changes the way that the AMD GPU handles page faults on the device. If you are working on Crusher actively, you've probably heard about this flag, and there's some complications around it. We're not going to talk about that really during this talk. I just want you to know that the reason I put this on this particular run line is it makes it a little bit easier for me to get a good, nice, clean, presentable trace. As I mentioned before, when the GPU crashes, especially if you are doing what I'm doing here, which is creating a crash that crashes every single process and almost every single GPU wavefront in that process, it can be a little bit tricky to get a nice clean trace out. And this is just one of those little tuning knobs that I fiddled with that gave me a clean trace. But in an ideal scenario, and we're working to refine this, you won't need to set this if you're not already setting it. Then I specified the ATP core file directory. So ATP is going to jump in after our application fails. It's going to do a whole bunch of heuristic analysis, and it's going to decide whether or not it can find any core files that would be useful, that it thinks would be useful for you to look at. And if it can, it's going to save them to this ATP core file directory. I've also specified here the ATP GDB binary. So this is what I need to do right now to get ATP to use a GPU, at the time that I made these slides, it was actually about a month ago at this point. This is what I need to do to get ATP to get GPU traces. I think in more recent versions of ATP, in the latest versions, it will auto detect. It'll look and see if your application is linked against a GPU runtime, and if it is, it'll try and do this automatically. But for safety, you can go ahead and just use this. So ATP is going to try and do it, but this will use the GDB that you specify to gather the stack traces for ATP and to process the core files. So in this case, I'm passing it rocgdb because I want it to be able to understand the GPU back traces, or understand the traces from the GPU kernels. And if I don't use rocgdb, if I just use regular GDB, I'm only going to get the CPU side state. Now, there's something important, a qualification that I need to put here, and I'll reiterate this pretty much every single time as we go through these slides, is the version of rocgdb that you are using needs to match the version of the ROCm driver that is installed on your system. So at this point on Crusher, that's ROCm 4.5.2. And the reason for this is that the debugging information and the ability to do debugging inside the AMD GPU kernel is very tightly tied to the driver version at this time. Again, this is all being very, very actively developed. And so you need to specify which version to use. And in this case, it needs to be 4.5.2. And now after all of that preamble and the extra special flags, there's the flag that if you were just doing CPU, is the only flag you would need to set, and that's ATP enabled. So you set ATP enabled equals 1, and this tells ATP that when your application crashes, it should jump in and try and do some analysis. Right. And let's look at what that gives us. So when ATP is invoked, in this case, the test job that I use for this is 64 ranks, and I injected a fault on every single rank at almost every single GPU kernel. And so in the gasp of those dying 64 ranks, we can see a whole bunch of these errors telling us that the application hit a signal. Remember how I said when things are particularly catastrophic, it may overload the ability to get a valid reason out of that. And you can see that happening here, and that our reason is unknown. And then we see what's the important line, which is that ATP analysis of slurm job, whatever is starting. So this tells us that slurm has obeyed our request and has handed off the state of the job to ATP and invoked ATP to come in and pull down and do some analysis. And then ATP kicks in, and what it's doing is it is crawling through the state of our application and the state of every single process in our application. And it's doing a whole bunch of analysis. It's compacting where it can. It's trying to find commonalities and condense things down. It's trying to find things that are interesting, things that stand out, that don't make sense, things that might be of interest. And it's trying to use a bunch of heuristics and select a subset of ranks to give you core files for if it can. So in this case, it picked a subset of ranks of the 64 ranks to dump core files to. But for some reason on my test system, for a reason that I'm still investigating and will hopefully have fixed in the near future, it was not able to actually dump those core files. And so this is a bug that I need to sort out in our implementation of ATP. So just displaying this for honesty that sometimes things don't work the way they want. But they did give us two useful things that we can still use to get good information out of ATP. And that is this ATP merged backtrace ... and this ATP merged backtrace _line ... Right, so what ATP has done is looked at the state of our application, pulled all of the stack traces, pulled the application state, and it has condensed it down to graphs that are written into a dot file that we can then plot. So it tells us what to do here, but to view those, we module load craystat, and then we stat view the ATP backtrace _line. And this kind of gives us, you can see we draw this graph that gives us the state of the application. So let's zoom in a little bit, and we can see here, so to decode this output a little, at the very top of this graph, we can see attached to the line, there's the number 64 : and then 0 to 63. So what this is telling me is that 64 processors have this node in their call stack. And of those 64 processors are processes 0 to 63. All of them have that node in that call stack. And then it breaks down from there. So if we look one layer down, right in the middle, where we have that GPU run 3x1, 12 processes have that in its call stack. And the 12 processes that have that are 15 and 16, 24, 27, and then some other ones that if this were a live session, we could mouse over and take a look. Right. And it tells us this is, at GPU run 3x1 faces share, which is a GPU kernel, line 131. And that's where that node is. And we can dive further down and see where each process is, both in terms of what source line it's at and what function it's executing. All right. And we have this for the entire application state, everything that ATP gave us. Now, in this case, I've opened up the ATP merged backtrace _line file, which is the version of this file that includes line numbers. Right, so it gives us the source location, and the line number. This is okay when we're only dealing with 64 ranks and where I have provoked to the fault at a single place, so that almost all 64 ranks are failing in pretty much the same way. There's obviously some divergence here, right? We don't have a trivial call tree, but we have it enough that we can at least make sense of what's happening. But if you have an application that has 20,000 processes or something like that, then you're more likely to have a lot of divergence, and you probably want to start with this ATP merged backtrace that doesn't include the line numbers. That's just going to give you a sense of which function, right, or which file your application failed in, rather than trying to give you the full application state down to line level, because there can be a lot of line level drift, even one or two on either side. Okay, and in this case, this has given us, this has located us down to where the error is in the application. So that's it for ATP. I'm going to check on chat and see if there's anything that needs to be asked still or answered, and then we'll go to stat.
So there was a question from Kevin asking how ATP is useful for hangs, and I just wanted to confirm. I replied the way it's useful is that you actually send your hanging program an abort, and ATP will kick in and present this.
Yep, okay. That's exactly it.
Okay.
So that's how you can use ATP for things that are not actually crashes, right? You can send signals and trigger ATP to come in and handle it.
Okay, so just to clarify, the onus is on the application itself to self-detect a deadlock?
No, so you could do it from outside, right? So you can instruct Slurm to, and there's a way to do this with PBS as well. I don't know it off the top of my head, but you can tell Slurm to terminate your application with a signal, and Slurm will pass that signal to the application. And so you could tell your application, I don't think a sig term will kick in ATP. You should check the ATP man pages. If you module load ATP and then man ATP, there should be information on what signals it'll handle in there, and you could send it, kill your application with a signal that ATP will catch. Okay. But you will have to have previously linked against ATP. That requirement doesn't change. I should say ATP is super low weight if you don't throw a signal, right? Because it's there in your dynamic link tree, and if you don't throw a signal that ATP catches, that is the only overhead of ATP, is that it adds an extra item into your dynamic link tree. And if you run to completion successfully, it's going to do nothing, right? That symbol never gets resolved. It's only when your application fails and the runtime or the job scheduler adds in ATP that then ATP goes into action. So it's one of those things that once it's enabled, we recommend running it on every application or every run. You may not want to do that for whatever reason, but it should be really lightweight and shouldn't interfere with you. So
it's basically just installing a bunch of signal handlers.
Yep.
Startup. Okay.
Yeah, exactly.
Yeah. The only reason I'm concerned about that doing it all the time is there's other libraries that also install signal handlers like Petsy.
Yep, exactly. Yeah, that is a characteristic thing. If you're going to use ATP, you probably want to disable Petsy signal handler, and vice versa. If you want to use Petsy signal handler, you should probably disable ATP. So that's a really good point. Okay, onward, upward, and accelerating.
Well, there's another question. So Stefan asked, do we have to compile with -G to get the line numbers in the doc files?
Yes, you do. Yeah, you will need debugging information. You don't have to go all the way down to unoptimized code, but you'll need debugging symbols at some point. So you could do a -G-03. You're not going to get as good accuracy, but you'll at least get the line numbers. And that's going to be true, I think, of everything that we talk about is if you want to get this useful information, and that's a good point, you'll need to compile with some amount of debugging information. Okay. So I said ATP can be useful for hangs, but the more useful tool for hangs is stat. So just check a couple things here. Okay. Oh, I want to go back. Where was I? Oh, okay. So stat. So stat is our most useful tool for hangs, and it can help you with both live locks and deadlocks. And I'll explain towards the end of the stat section how to differentiate how you can use stat to tell whether you have a live lock or a deadlock. So stat is something that doesn't require any special compilation. You know, for the most part, you could get by with stat in most cases, even if you don't compile with debugging information. You're going to get much better results out of stat if you compile with -g. But even without -g, we can most of the time figure out roughly where, there's some amount of information that goes in, but you should just compile with -g and it'll be better that way. So with stat, but other than compiling with -g, you don't have to do anything special. There's no extra libraries you have to link. You just run your application and your application executes, and then your application stops executing. And you go, oh, wait, my application should have finished 10 minutes ago. It's still running. Why is it still running? So you can just module load Cray stat on one of our machines. You will need, for the way that I'm going to show you to do this, there is a command line interface that you can use. You could do module help, do a man stat _CLI to do that. But I'm going to show you how to use the GUI here. If you're on a system, I should point out, even if you're not on a Cray system where Cray stat is available or where Cray PE is installed, stat is a tool that Livermore develops, right? And we're actually downstream from Livermore, that we maintain it and make sure that it runs on our systems, but the main stat developers are Livermore. And so stat is freely available and you can find it in a lot of places. This should be useful elsewhere as well. But stat, you can just load it up. And we're going to use the GUI. So as a general recommendation, if you can use VNC, you should. I meant to check before this talk whether or not there's any way to do that on the Oak Ridge systems. I don't know that there is, but I forgot to check. So if somebody in the chat knows, they can post it in the chat and let everybody know. On my systems, what I'm going to show you is used out of a VNC. If you don't have the ability to use a VNC instance, you'll need to SSH in with a tunnel, or SSH-X to tunnel X over SSH, right? And that you're going to see some lag from that, right? We've all used GUIs over SSH before, and it's not necessarily great. But okay, so we have hung. I'm going to go into VNC, or go into a VNC. I'm going to start stat. And that's going to give me some backtrace. So here's how I'm going to start stat. So to get stat to recognize the GPU state, execution state, I need to start in a particular way. Just like with ATP, we specified the ATP GDB to use. Here for stat, we're going to tell it to specify we wanted the stat GDB to be ops ROCm 4.5.2 bin rocgdb. So again, this is done on a system with the 4.5.2 driver, and so we want to use the 4.5.2 rocgdb. You could specify this, and I'm going to say everything that I'm doing here on the command line, including specifying stat GDB, you could do at the configuration step here on the right-hand pane in the GUI. It's just, I find it's a lot easier to do it on the command line. Okay, so I do stat GDB to tell which GDB it should use. And then I tell stat GUI is the command that I want to run. The -G tells stat to use a GDB backend to attach to processes in trace rather than any alternative backend it might have. And we need to use the GDB backend because we need to use rocgdb because we want to get AMD GPU traces. And then I'm going to pass this W option, which is going to tell it that I want to trace threads. If I don't pass -W, or if I don't tell stat that I want to trace threads, it's only going to give me the trace of the main process. So for an MPI application that's across 7,000 nodes, that may be enough. You may just want to know, am I stuck in an MPI call somewhere, or is there an MPI barrier or something that's happening? And in that case, you may want to not trace threads. But in my case, again, I want to get GPU state. And so if I want GPU state, I need to trace threads because the GPU state shows up as threads. And then I'm also going to sample line numbers in this case as well. Again, both tracing threads and sampling line numbers are things that you should use with caution, because the more variation there can be, the more parameters you allow to vary between different processes or different samples, the more variation you're going to get in the tree. Okay, so when I pass these options to start the GUI, that means everything is set up the way that I wanted initially. Stat, I'm starting this on the same login node that my job is running on, and it looks and it checks, oh, here's the Slurm process that, or here's the list of Slurm processes that I see that belong to you. I could put this on a remote host if I wanted to. For example, if I'm logging into a multi-login system using SSH-X and I need to have it search a different host, I may need to give it a different host name, login2 or something, to try and find where I'm actually started the process. And I can see that it's Slurm, or I can see the srun command. I'm going to click on it and select it. I want the top one in the list, right? Because this gives me the command I actually ran, and then the fork. So I want the one that I actually ran, and then I can just click attach. And when I click attach, stat reaches out through the job and attaches to all of the processes, and then it pulls the state that I have asked for, and it displays it as a graph. So again, I'm going to zoom in here, right? And I can see it's the same sort of syntax. I've asked for threads here as well. So I'm going to get some thread information in addition to process information. So this root node, this gray root node, 64 processes are in that gray root node and 480 threads. That's what the parentheses mean, is that's threads. And then of those, it tells me that the processes that are there in the square brackets are 0 to 63 are there. And then and then 64 and 32 threads. So, okay, you can see this is following the edges down, right? And so there's another edge over there that's kind of impinging on my text. But I can see the 64 processes and 480 threads total are pointing at this orange node, this maroonish node, this GPU run 3x1 faces share with this line number 185. And yes, that actually is the real location of the bug, right? So doing a stat sample with line information was able to give me that real location, and it's because there's a while loop there. Right? And that's why it's on. So just a few notes on the stat screen. This is really something that you should come in and play around with and look at your options. There's a few options here. So we could just click the detach button. I don't have an arrow pointing at it here, but you could detach. If you sample your application and you go, oh, no, actually, okay, it's just running really slow, or, oh, I forgot I ran case XYZ instead of case BCD, then you can just detach and let the application go back to doing its thing, and you don't need to worry about it. But you can stay attached and let the application can resume execution too. So you can just click that resume button, and stat is going to let the application start running again, but stay attached. And then you can wait a few minutes or a few seconds and then click the sample button again. Right? And you can sample and you can change options if you want. Maybe you sampled with threads on, and that gave you way more information than you cared about. So you want to sample again, but turn threads off. You can click that sample button, change configurations, and do another sample. And that's one way that you can tell if you're in a deadlock or in a live lock, is that you can look at stat, you can see where you're at in the code and go, I can't tell from the source alone whether I should be progressing here or not. And so you unpause and keep going and let stat run, and then pause it again and take another sample and see whether or not your state has changed. That's one option. The other thing that you can do is use this sample multiple button. So this is really the good definitive way to test whether you're in a live lock or a deadlock, is press that sample multiple button, and that's going to let you set up some series of samples spaced some amount of time apart. So you could set up, for example, 10 samples spaced about a minute or two apart, and those will step through, pull information, and you're good to go. All right. Are there any questions on stat? Looks like chat is empty, so I'm going to push on. Oh, go ahead.
So when you say the multiple, is that for the same task or thread, or for multiple threads, multiple tasks?
So that is for the same application, so the same job. So it'll take what sample multiple means here is take multiple samples. So it'll take a snapshot of your application and then let it run for maybe 10 milliseconds or however long you specify, and then take another snapshot and then do that, repeat that 10 times. So you get a time series of your application state.
Oh, okay. So it's for all the threads and all the tasks, but at different times. Okay.
Yeah, exactly. Okay. Okay. So there's those are the two tools that you can really use to get a good picture of your application state. Now let's talk in more depth about a really valuable tool that can be a bit overwhelming. And it's hard for me to give you really clear examples of how to use this, but I want you to be aware that it exists. And that is the ability to debug using runtimes. So I call this sipping from the fire hose, and I think it should be pretty apparent why in just a moment. So let's start with the Cray OpenMP and OpenACC runtimes. So the Cray OpenMP and OpenACC runtimes have built-in logging information that you can turn on demand that'll write the standard error. We have 3 settings. You can set Cray CC debug equals 1. This is the good place to start. It's going to tell you in a very concise way when we launch a kernel, when we do a set of data transfers. Make sure this is a good way to tell that your application is running and actually offloading the way that you expect. That maybe a section of code is actually executing and offloading the way that you intended it to, but it's not going to give you enough information in most cases for really complex debugging. The value that we recommend most users start at if you're going to try and use the runtime to debug is 2. So this is intentionally designed by our compiler developers to be user-friendly, to present information in an easily readable and concise way. And it's going to show you what the runtime is doing, but it's not going to show you the really, really fine-grained nitty-gritty details on what the runtime is doing. Right? So you're not going to see a bunch of address ranges and pointer dope vector contents and things in 2, but should be still pretty helpful. 3 is extremely verbose. It's not generally designed for everyday users, but if you have a need to use it and you have the expertise to use it, it's extremely, extremely valuable. So this is going to give you really, really detailed information on what the runtime is doing. This is the level that I turn to when somebody comes to me and says, I think I have a OpenMP runtime compiler bug, or that the Cray compiler has an OpenMP runtime bug. I'll turn this on, I'll look and do some parsing. But generally, you as a user probably want to stay away from this. So let's show kind of an example of how we can use the OpenMP offload runtime to debug. So this is a version of Faces running on the AMD GPUs, MI250X, using an OpenMP implementation. This is the Fortran version of this code, I think. So here's my run line, right? I've launched Faces, I've get it set up, and I get the wrong answers, right? So I've run here. I'm just doing a test case where I run on a single rank. When I turn on that runtime debug variable, it's going to turn it on for every single process in the job, and that's going to be some pretty overwhelming runtime information. You can write wrapper scripts or use slurm commands to redirect that output to different locations, or to only turn on that environment variable for 1 or 2 ranks and only get the output from those ranks. But if you try and do this across a big job, it's going to be overwhelming. So I'm going to trust that if you have the expertise to use runtime debugging or use these runtime debug messages, you have the expertise to figure out how to either turn them on for one process or selectively turn them on or catch the output. But you can also reach out to me for tips or tricks, and I'm happy to help you in your particular case. So if I just run this normally without the debug output on, and I get a wrong answer, right? The application failed. So we want to find out what went wrong. Let's see if we can find out what went wrong using runtime debug information alone. So I'm going to turn the faucet on a little bit. I'm going to turn it up to run or ACC debug equals 1. And this is going to show me, as I mentioned, right? It tells me really in a very coarse-grained way how data and kernels are being moved, what the runtime is doing. So it tells me that there is some OpenMP construct of some sort around line 109 of the file faces.f90. And associated with that OpenMP construct, there's a transfer of 7 items to the accelerator accounting for this many bytes. And there's no transfer to the host in that construct. Right. And then it tells me the same thing for a different location. It also tells me when it launches a kernel. It tells me when it synchronizes on that kernel and where in the source code that it does that. And it just gives me these very coarse-grained, when I encounter an OpenMP item, what is happening when it does that. Okay. And then, here I've done, this is the startup. This is the initial indication stuff at the very top. And then I put a line and we can kind of see the bottom. So if you're clever here, the reason for the bug is actually already apparent at this level of information, but I'm going to hold out to the end and you can look at these slides as we go along and see if it shows up for you. All right, let's turn this up to ACC debug equals 2. And now I'm only going to show you the end of the application, the very last things that get printed. So here, this was at line 901 was the last transfer here. There's a synchronization and then line 908. And here you can see, we're only really showing you line 908 and then that 876 up here. Right, so we're getting a lot more detailed information now. It's telling us specifically what it's doing. So it's telling us which kernel it's launching and the line numbers. It's telling us how it's launching it. It's launching it with 1 block and 1 thread. In this case, it's telling us, what explicitly is being transferred and how big each of those transfers are. And we're getting that because we have debugging information on. If we didn't have -G, we wouldn't be getting all of these symbols, right? And we're getting some, some of these symbols are maybe a little bit unique looking. This is the perils of runtime debugging, is that you're also seeing how things are represented in the runtime, which may be simple names that aren't particularly meaningful to you. And then we can see when it releases the information. All right. And again, it should be pretty there. If you're clever, we can actually see the bug maybe at this line, but I'm going to push on a little bit more just to see. So this is really what we recommend for most debugging. If you're going to dip into this, is this level. If I turn this up to 3, you can see how much more detail I get. All right. So this is telling me very, very, very explicitly. Let's dig into the second transfer. It's telling me I'm transferring the state vector U that has these dimensions and this many bytes. It's telling me what the host memory address of that is, which in Fortran is something really unusual. There's a set of flags here that are representative of some things internally in the runtime. It tells me the host pointer range. It tells me its present table index and how many references it has. And it tells me when it was released and what its reference count goes down to. And then it also tells me its accelerator reference values. So remember when I said when we see those GPU memory faults and they give us an address where the fault occurred, if we're working in OpenMP, we can come and take a look at this debug information and figure out where those addresses are with respect to the information that the runtime gives us here, and actually get some really useful debugging information out of that. But this really explicitly shows the bug, which is that for this state vector U, which again, if you knew the code, you would know is the state vector, we're just freeing it, we're releasing it. We're not doing any data transfer of this item back. Right. And so we should probably copy that state vector back. And of course, the bug that I introduced here was instead of having this be an OpenMP map to from U, instead it's a map to. All right. So that's just one way that you can use the runtime to get this information. There's a whole class of bugs that you can use the runtime to get really useful information from, especially when it comes to, for example, if you're using enter and exit data constructs, where you maybe enter data, a variable, and forget to exit data before you free it. That would show up in the runtime as a overlapping present or overlaps, but is not contained within sort of error. And I'm sure some of you on this call have seen that before. This runtime information can be really useful for debugging that. So this is the Cray OpenACC runtime. I'm actually really, really proud of what our compiler team does for this runtime information. They really do a great job of trying to surface it at 3 different levels for different use cases and making it be accurate and useful. And I've written a lot of scripts that parse this information, and I've used this information pretty regularly to solve a whole host of bugs. Costas, who is in the chat, has used this information to solve all sorts of issues with Fortran pointers and attachment issues, some of those compiler bugs, some of them application bugs. This can be really, really, really useful information in the right hands, and you can spend some time pondering it and see if those hands are yours. The AMD runtimes also provide similar information. So the AMD OpenMP target runtime provides information in the same way as the upstream LLVM OpenMP target runtime does. So there's a link here on this flag. I think the slides will be made available at some point if they're not already available, where you can click on this link and go read the LLVM documentation on the libOMP target info flags. And you can set the environment variable libOMP target info to control what is printed, but not how much is printed. So that's the difference, right? Our runtime, we don't give you control over what gets printed, at least not at the environment variable level. We might actually in runtime calls, but at the environment level, we don't give you control over what is printed. We'll print everything, but we will print it at different levels of verbosity. Whereas libOMP target info, you have no control over verbosity, but you have control over what gets printed. Like most flags that we will deal with both in AMD and LLVM land, this is a bit field. And so if you want to get all of the debug information, you can set it to -1. That's going to give you a series of 1s, and your bit field is going to be fully populated. There's also a separate debug runtime that you'll see some documentation for at that link. That's really for library developers, and this is really low-level stuff. And so if you need it, it's there. And there are some instructions to build and link with it. You have to link against the libdebug versions rather than the standard versions. But it's really verbose. It's really low level. So because the version of Faces is OpenMP versions of Faces are not particularly well maintained, AMD's compiler was not able to build and correctly run the C and C++ version of OpenMP Faces, but it can. I just wanted to at least show you what this looks like, so I just built a simple sample out of the AOMP samples directory, and you can see what libOMP target will give you, which is still very clear, good information. Right, this is still really great and useful debugging information. Just to give a slight taste of why I don't really recommend you use the OMP target _debug version, this is what you get for the target debug. Right, so this is the same application as the one that we just looked at. This very, very simple example, and it gives you really, 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 really detailed information about what the runtime is doing. You can also get the same thing out of the AMD HIP and HSA runtimes. This really, really, really is a lot of information. And this is the sort of thing that if you think you're chasing a runtime or a compiler bug, you may need to look at this, but in the most part, you're not going to look at it yourself. Again, you can kind of turn up the verbosity or the types of errors that get changed here. So if you turn it up to 4, you're going to get fully print detailed debugging information. If you turn it up to 1, you're only going to get what errors. There's some documentation here in AMD's HIP documentation that's really useful about how to use this runtime debugging information that you can go read if you'd like. AMD also provides a knob that you can use to tune what gets printed, and that's this AMD log mask. All right, so here's an example where AMD log level helps a whole bunch. So if you go to run on Crusher and you get this error that says HIP error, no binary for GPU, unable to find code object for all current devices. This is a pretty common error when you first hop on the system if you're not really sure what you're looking for. So let me turn on log level and we can see pretty explicitly what's happening. So what's happening is the runtime is going to try and load up a kernel to run on a device. The device that it sees are GFX 90As with a certain set of flags, SRAM, ECC plus, and XNAC minus. And what it finds inside the application that I started is only a GFX 908 binary. So somebody built this code for MI100 instead of for MI250X. And that tells me right away, oh, I need to go build correctly for GFX 90A. right? So this is a really quick, easy way to tell what you built for and what you need to build for to get your code to run. But really, again, turn this up with caution. If I turn this same really simple thing up to 4, I get really detailed information about what the HSA and AMD runtimes are doing. So this can be really overwhelming unless you really know what you're looking for. Here's just another set of environment variables that I find to be really useful for debugging race conditions. And just when you sort of need to slow things down. So the first of these is AMD serialized kernel. So again, this is a bit field. 1 will synchronize before kernel launches, 2 will synchronize after kernel launches, and 3 will synchronize both before and after kernel launches. And AMD serialized copy does the same thing, but for copies. All right, so here's some other links that you can go look at, again, to figure out some AMD flags. I'm going to show just a really quick example of how these synchronization flags can be useful. So here's a case of me running faces across 4 nodes with 4x4x4 GPUs. We're running to completion. We're not crashing, but we're getting the wrong answers. So can we figure out why we're getting the wrong answers just by using environment variables? So the first thing that we should do is just slap on full synchronization, right? We'll synchronize before every kernel launch and after every kernel launch and before every copy and after every copy. And if I do that, I get the right answer. Okay, so this tells me that I have some synchronization issue involved in the GPU. Can we get better though? Can we narrow it down more? So I know, because I know faces, that faces doesn't do very many host device copies. So instead of synchronizing after host, like, can I rule out that the host device copies are the source of the synchronization error? So to do that, I just don't synchronize after copies, right? I will only synchronize before and after kernels, and I won't synchronize around copies. If I do that, I still get the correct answer. So this means that my synchronization error probably is not occurring after a copy or before a copy. It probably has to do with the execution of a kernel. Can I narrow it down even more? Well, let's try just setting AMD serialized kernel equals 1. So this synchronizes before every single kernel launch. So what does this rule out? This rules out the possibility that I have 2 kernels that are operating on the same data that are racing, right? If I turned this on and I got correct execution, that would probably mean that I have 2 kernels that are racing each other, and when I synchronize and prevent them from running at the same time, then I am getting correct answers. But that doesn't happen in this case, right? So we probably don't have 2 kernels that are racing. If I synchronize after kernel launch, what I'm saying is I want to wait for every kernel to complete before the CPU continues executing. And so when I set serialized kernel equals 2 and synchronize after kernels, and I get the correct answers, this is the minimal set of synchronization that gives me the right answers. And that probably tells me that the CPU is consuming data before the GPU is done. And actually, that's what's happening, is that I commented out a hip stream synchronize, and that is giving us the right answer. Okay, in the very few minutes that we have left, I'm going to talk about the art of active debugging. Now, you'll notice that this has been, at this point, almost an hour and 40-minute talk, and I am just now getting into the debugger. That's really by design. I want you to have all of these techniques, have all of these tools, and not feel like you have to use the debugger. I really encourage you to use the debugger and learn how to do active debugging, but it can be a bit intimidating. So you have a lot of tools at your disposal to debug even before this. So just a mention of rocgdb. Rocgdb is a great tool, but we're going to quickly throw it in a GDB for HPC harness. So rocgdb is a version of GDB that AMD has added a whole bunch of really important debugging tools in to debug on their GPUs. It has all of these great supported features and has each wavefront in the debugger is going to be represented as a single thread, and we'll see that here in just a second. But it does have a few shortcomings. It's not multi-process, or at least not more multi-process than GDB already is. There is a way to debug multiple processes in a single GDB instance, but you can't do that across multiple nodes, which is really what I'm after when I say multi-process here. There's a limitation that I already mentioned, which is the debugger version must match the version for the GPU debugging. Otherwise the driver version, otherwise you can't get GPU debugging. And the native thread representation can get a bit overwhelming. Let me show what I mean by that. So here's an example of rocgdb. Here I run faces. I'm running it on a single process instance. I go ahead and run it. Faces takes its command line arguments from standard in. So here, this run with an arrow opt-in says read the command line arguments out of opt-in, or sorry, read standard in out of opt-in. These aren't command line arguments. This is standard or standard in. And I run that in rocgdb. I can run until I hit, here I've set a breakpoint. So I can just run until I hit a breakpoint in a GPU kernel, and that gives me the state. Now, if I want to see the GPU thread state, I type info threads. And info threads is going to print both the main thread, thread 1, and it's going to give me the a helper thread, thread 2, that's in the ROCm runtime. And then it represents every GPU wavefront as a thread. So I've truncated this here, but if I have 1,000 wavefronts running, I'm going to have 1,000 threads here. That can get pretty overwhelming to look at. But despite that, there's a lot of regular GDB goodness that works really, really well here, right? I can info threads, I can move around, I can move to a thread, I can print back traces, print in newer versions, print symbolic variables. I can set watch points. I can use the layout command, which is a command that I learned in an AMD tutorial, which is really awesome. So here, if I do layout ASM while I'm on a GPU thread, I can see the current program location and also view all of the assembly. And I can actually even single step through this GPU assembly execution on the device, which is pretty awesome. That's really cool. But despite that, it does get overwhelming. And we can't go off node and have parallel processes. So we have GDB for HPC that will help us with that. So GDB for HPC is a tool that we provide that's really a parallel harness and aggregator around your debugger, around GDB, rocgdb, or CUDA GDB. I really recommend that you load the GDB for HPC module and do man GDB for HPC and kind of read the introductory documentation that we have there. And when you're in the debugger, you can also do help info threads or help info whatever, and that will, help whatever, and that'll give you information on a command. GDB for HPC supports both launching and attaching. I mostly just launch, so launching is what we're going to do here, but you can see the man pages or the help pages to learn how to attach or how to integrate into a batch script. So here's my launch line to launch faces on GDB for HPC. Here I'm going to launch process set A with 16 ranks. So what do I mean by process set? So when you're inside GDB for HPC, you have the application that you're debugging or the instance that you're debugging, we refer to as a process set. And that process set is described by an internal debugger variable that you specify, right? So when I say $A, I am telling the debugger, this is a GDB for HPC variable A, that describes the process set, and the curly braces, or say the curly braces tell me how many processes to put in that process set. So when I say launch A16, I am saying create a process set that has 16 processes in it. So this is like saying -n on your Slurm runline or your MPI runline, right? This is how many processes I want to launch. Then I do --GPU. And that tells me how many threads, it tells me that I want to use the GPU debugger. And GDB for HPC is going to, by default, use whichever GPU or whichever version of rocgdb it can find in your path, which is why I'm not explicitly specifying GDB path here. I can set any environment variables that I want to here. If I want to set additional environment variables, Faces uses GPU aware MPI, so I need to set GPU aware MPI. And then -G is job launcher arguments. So these are the arguments I would otherwise pass to Slurm. I'm telling it I want 2 nodes. I'm telling it what partition I want, and I can specify things like CPU binds and masks here as well. -in tells me which file should be passed to standard in. As I mentioned, Faces reads input off of standard in, and so I want to give it -I. And then I give it the binary that I want to debug. This is just this particular case that I need to launch Faces for GDB for HPC. I could use help launch instead in GDB for HPC to get all of the debugging or all of the information on arguments, which did not make it into this deck, unfortunately. I thought I put it into it, but it must have not made it before the cutoff. So you can go ahead and go into GDB for HPC and do help launch, and that will show you how to, for example, pass arguments, command line arguments, not just standard in to the debugger. So here's an example. I do GDB for HPC, it starts it up. I do this launch. I say I want to launch process set A with 16 ranks on a GPU with this environment variable set using these batch arguments and this input file. And we can see GDB for HPC start up. So it starts up MirrorNet and hooks itself up to all of the nodes in my job. First, it gets an allocation from Slurm, and then wires itself up, starts debuggers, and then attaches itself within the debugger. And we'll see this countdown. It'll take some time as GDB for HPC wires itself up, and that tells me, okay, all 16 of my processes are connected. And then it runs until it halts in the initial breakpoint. So for MPI applications, the default initial breakpoint is inside MPI init. And so GDB for HPC, the launch will run until I hit that initial breakpoint. All right, then I'm going to go ahead and just let it run. I'm going to set that breakpoint where I set it before when we were looking at rocgdb. And I'm going to go ahead and let it run. And it hits that breakpoint. And when I hit that breakpoint, I'm going to do info thread. And info thread really showcases why GDB for HPC is a useful tool. So before I showed you rocgdb with a single process and a whole bunch of threads, and it was really overwhelming. Now we're actually looking at 16 processes and just as many GPU threads. And you can see that GDB for HPC is aggregating all of that information. Right, so it looks across all of these processes and it says, oh, processes 11 through 12 and 14 and 15, all of these threads 4 through 2,313 on all of those processes are in the same spot. They're at this line, they're at this breakpoint. And so it aggregates them all that together and shows me exactly where I am. Right. And so this is really the power of GDB for HPC is that it lets me launch and execute in parallel and also aggregate things. Unfortunately, the aggregation does sometimes break down. We can see the breakdown in aggregation here. Again, this is whenever we see this and we're actively trying to refine it and improve it and make it better. All right, I want to give everybody at least a little bit of a break. So we're going to real quick kind of pop through these techniques. And I want you to come back to the slide deck later when you're ready to use GDB for HPC and look through these different techniques on just tips for using GDB for HPC. So the first thing in GDB for HPC is that by default, we're looking at the entire process set. There's a way in GDB for HPC to focus down, and we can do focus down to a specific subset of processes. And so this is technique number one, focus on what matters using the focus command. Technique two is we start up by default in nonstop mode. This is really, really useful when debugging on GPUs because in nonstop mode, we can hit a fault on a single GPU thread and the rest of the GPU threads will keep executing, right? So we can really pinpoint exactly where the error is because we can see what's running and what's not running. You can also just stop everything if you need to. And so if you want to look at the state of all the threads, including the ones that are still running, you can just halt everything. GDB for HPC only surfaces a subset of commands. And the reason that it does that is because some information is really, really hard to aggregate, right? If I go and I print a memory address across 20,000 ranks, that the chances of that memory address aggregating well and being the same on 20,000 ranks is really, really, really slim. So GDB for HPC tries to only surface commands inside the GDB for HPC interface that aggregate really, really well. For example, info args does not aggregate well. In general, the arguments are going to be very different. And so we generally don't surface info args inside GDB for HPC. But whenever you're in GDB for HPC, if you want to drop down to GDB mode, you can get access directly to GDB and still have that parallel harness and aggregation. But generally, I recommend only doing this if you know for sure that what you want to print is either going to aggregate well or is something that you're going to focus in before you do it. So here, I want to print the arguments. GDB for HPC doesn't surface it. So instead, I'm going to drill down into GDB mode, enter GDB mode. I'm going to do info args. It's going to show me the information. I've trimmed a lot of it. This showed separate information for every single rank. And then I can just do end, and that'll take me back out of GDB mode. Okay. Finally, some things you can inline into GDB mode. So for example, here, when I tried to print this string of values in this array, GDB for HPC said, I don't understand that syntax. And I put quotes around it. And those quotes tell GDB for HPC to evaluate an expression in GDB mode. And that lets me do that. And then I guess this is just the last one. You don't have to focus. So if I only want to print a subset of ranks, there's a syntax for doing that. And you can come back at this slide later and look at it. Okay, so here's the debugging takeaways. And then we'll let you take a short break before Trey dives in. So the big takeaways that I want you to have, first of all, debugging is easy when you're introducing synthetic bugs. That should probably be the #1 takeaway from this talk. I found the bug every single time I went looking for it, and that's because I introduced them all. It's really, really, really important to understand what your bug could be before you go looking for it, right? Really pay attention to the error messages that you're getting out of your application crashing, and really try to understand what's happening before you start looking for your bug, and understand what the possibility space is. Understand what sort of tools are at your disposal and when they are useful, right? You don't have to know how to use every single tool that I showed you today, but I'd like you to know that they exist. And so that when you need them, you can reach for them. And really, something that you really, 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 really should remember is that every debugging session is a learning experience. If you knew where your bug was, you wouldn't need to debug, right? So really go into debugging expecting to learn something both about the way that your application functions, the debugging tools at your disposal, and the way the system itself operates, and really try to view this as a research project. So when you see a bug, when you see something that doesn't work the way that you expect, try to view it as researching the thing that doesn't work. And I think that changing your attitude on that can help a whole lot. And then there's a whole bunch of tools we didn't talk about here today, address sanitizers and thread sanitizers. And I didn't mention Valgrind at all, which is one of my favorite tools. And the reason for that is when it comes to debugging on GPUs, a lot of these tools are in flux. And so we'll hopefully be able to talk about them in more depth later. I'm very full over time. I think we'll take a break now. Trey, when do you want to start up?
I was thinking 5 minutes after the hour.
All right, we'll start 5 after the hour. That should give everybody a chance to use the restroom. I will hang out here and answer questions if anybody has questions now. And you can always reach out over email and we can talk. So the slides should be posted on the ECP Confluence, is my understanding. I don't have access as a vendor. I don't have access to all of the slide locations, so I can't tell you exactly where. If you aren't able to find them on there, feel free to reach out to me and I'll provide you with them.
Okay, Steve, I'm going to start sharing. Are my slides visible?
Yes. Yep.
Great. I'm mentioning this mostly for the recording. So 5 minutes after the hour is 5 minutes from now.
Hola. ¿Cómo estás, Nala?
That was
Somebody's
interesting.
unmuted.
That sounds like the effects of a week-long ECP all hands meeting.
So it's 5 minutes after, but I'm gonna give it 1 more minute. So when my laptop says 6 minutes, get started. Okay, 6 after. So my name is Trey White. I'm in the Frontier Center of Excellence with HPE. And I'm going to start on part 2 of our tutorial. This part about performance profiling. So in part 2, I'm going to start with Perftools and how to visualize the output of Perftools with a tool called Apprentice 2. Those are both tools from the HPE Cray Programming Environment. Then I'll cover Rocprof from AMD's ROCm Environment, in particular, how useful it can be for tracing. And then I think we'll still have time for the bonus topic, which will be diving into assembly code. First, I want to thank OLCF for the use of Crusher. So all the slides that I'm going to present, I actually ran on Crusher using available software there. So it should all work for you if you were to try the same thing. So Crusher is a system with AMD MI 250X GPUs. There's 4 of them on each node. And if you want more details on the layout of Crusher, they have a great quick start guide. And here's a link to it above, or you can see the address here for more information. So let's dive in. I'm going to start with Perftools Lite GPU, and in particular, I'm going to show you how to use it with 2 compiler wrappers, both the Cray Programming Environment and the HipCC compiler with Rocprof. So here's a representative build. I'm going to use faces for these examples. This is a representative build with progenv AMD environment, where the first thing I did was load progenv AMD, which takes the CCE wrappers, the Cray compiling environment wrappers, and uses them with the AMD client compilers. So by using these wrappers, you get the HPE Cray MPI environment automatically. You don't have to figure out the include and link arguments. And you also get the latest HIP optimizations from the AMD version of the client compilers. I add the module Cray PE Excel AMD GFX 90A, where the GFX 90A is reference to the instructions set for the AMD MI 250X accelerators. So because Faces uses GPU buffers with MPI, I want to make sure that I'm using the right connection with the right accelerators. To use HIP, I load the ROCm module and I use the -x HIP argument to the compiler. And right now we still need to add a library with a link path there using the ROCm path environment variable. So that's how to build. And then to run it, this is what I used, where I typically use a build script and a run script so that I always match my environments. And so it's important to match the build environment when I run. Again, because Faces is going to be using GPU buffers for MPI, I need to turn on that support in MPI. On whatever system you're on, you need to carefully match all the various parts of the architecture. And in particular, this is the set of commands that are particularly effective on Crusher today. Some of this might get more automated in the future, but today this is what I used, where I'm making sure to spread my 64 MPI tasks that I'm going to run across the 4 NUMA domains that are on the host CPU, and across the 8 accelerators. So there's 4 MI250Xs, but they present themselves as 8 different devices, and across the 4 network interfaces to the Slingshot interconnect. I want to spread everything across that, and this is how you do it. So now let's look at the changes that are necessary to use Perftools Lite GPU. First, you need to load the Perftools Lite GPU module, just add that. So right now there's an issue with that module, and there's a small workaround that with a path change that I've listed here. Hopefully that won't be required for long. And then when I run this, it runs just like before, except at the end, there's one extra line saying that Perftools instrumented my executable. Now to run, I need to match my build environment. So I add that extra module line, and then I get a whole lot of extra output. I'll dive into the details of this output in a minute. So let's look now at building with HipCC instead of the Cray compiling environment. Here I load the module ROCm. I don't need the progenv module, and my compiler is HipCC. And to target the MI250Xs, I add the Cray PXL AMD GFX90A, primarily for MPI. And I also need to tell HIP what my offload target is with the offload arch. And these extra environment variables fill in the necessary stuff to make sure I get the right libraries in the right places to use HPE's Cray MPI. To run it, I don't need a progenv AMD. Otherwise, it's the same as running with the CCE version of this example. Now here's how I build to use Perftools Lite GPU. I need to add the module, as you'd expect, but then there's all this extra stuff. And this is because we're not using the Cray compiler wrappers that would automatically add all these options. Instead, Perftools provides this command called pat_ops that gives you the compile and link arguments. So if there's a software upgrade and these arguments ever change for Perftools, this pat_ops command will change for you, so you don't have to change your build environment code. So if you look at what the pat_ops command takes as arguments, first there's the build phase of the compiler and the compiler you're using. And then if you're doing a so-called light experiment, which we are, GPU, you add that argument here. So here we have post-link, pre-link, post-compile, pre-compile, and include files to add to the build. Then when we run this, again, there's an extra line confirming that Perftools did indeed instrument our executable. To run, I add the module load Perftools Lite GPU and get lots of extra output. So now let's dive into that output. So first there's a header file, or not a header file, a header paragraph that tells you the version of Cray patch you're using and how big your run was and when it executed and so on. We get some IO and memory stats. So Faces doesn't do much IO, so there isn't much of interest here, but for real applications, this could have more interesting content for you. And then let's get into the guts with table 1, the profile by function group and function. So first to note that there's nothing below 1% listed because it hides that by default. It takes data for everything, but it shows in this table functions that take more than 1% of the host's runtime. We have these 2 columns called imbalance time and imbalance time percent that are there to show you the possible load imbalance. So the imbalance time is the maximum time for any single task minus the average time across tasks. And we use that to compute the imbalance time percent, which is the imbalance time over that maximum time times the number of tasks divided by the task minus 1. So what that really means is if you have 100% imbalance time, it means only one task spent any time in that function. 0% imbalance means all the tasks spent exactly the same amount of time. So here we have the HIP calls. This is the host time spent in HIP API calls, not the kernel execution times on the accelerator. We'll get to the kernel execution times a bit later in the talk. Then we have the MPI time that is spent doing point-to-point and what I'm calling the active work on collectives. That's to differentiate from this MPI synchronization time. So one thing Perftools does is for any collective communication, it puts an implicit barrier and measures the time it takes for all the processes to get to that barrier, and then times the collective separately. For faces, the only collective is in fact a barrier, so it's a barrier followed by a barrier. So this isn't as useful. But if you're doing, for example, a big all-to-all or something that can take a significant amount of time in and of itself, it's interesting to separate out the synchronization time so that you can see if that long amount of time was because of a load imbalance versus a long amount of time because of the actual MPI operations. Then Perftools sticks in this observation where it notes that it looks like there's a 4x4x4 grid and there's a lot of time being spent in MPI. And so it might benefit you to reorder your ranks, your MPI ranks. And it produced a file called impitchrankorder.grid, and that allows you to do that reordering. And so when I saw this, I was like, hey, let's give it a try. I actually want to see if this thing works. So let's try impitchrank reorder, or impitchrank order, pardon me, is the name of the file. Let's see what happens. So this is the actual file it produced, and it's got some comments at the beginning that tell you how to use it. So you copy it to you copy this impitchrankorder.grid to a file named impitchrankorder and set an environment variable to 3. And in addition, it tells you how it actually generated this file. There's a Perftools function called grid order that allows you to create your own files. So here's how I tested this feature. First, I did an salloc to get a fixed set of nodes so that all of my runs would use the exact same nodes. And then I did 2 sets of 3 runs to take averages. So an average over the first 3 versus the second 3, where the difference is for the second 3, I copied that impitchrankorder file, set the rank reorder method to reorder the MPI ranks. See what happens. So it did a thing. It was a little bit faster. This is a small run, so it was just a 2% improvement, but it at least illustrated kind of how to use this, and that for when you're scaling over a much larger machine, this could be a benefit to you. So now let's get back to our output. So that was table 1 and an observation. Now we go to table 2, which gives us the time and the bytes transferred for accelerator regions. Note that the ordering is by the first column, which is host time. And in this code, the host spends most of its time waiting for the accelerator, which is a good thing. If you're trying to use accelerators, that means you're spending most of your time on them. But it's not particularly relevant in performance profiling. And so in this listing, we do have the amount of accelerator time spent. And ironically, it is the last of the kernels listed. Next comes table 3, which gives us some energy and power usage. I'm not going to dive into this much. And table 4, the file input stats by file name. And so with faces, there isn't much input. As Steve mentioned, it uses some standard input. The first thing it does is all 64 tasks check in with HIP. And so you see where they've pinged the file system there. Then we get standard input, which faces reads from the first task and then broadcasts it. And then you get all this stuff, which is AMD's code object manager, getting the code ready to put on the GPUs. So because there isn't much IO in this code, it's dominated by these very small things. If you have a code that does a significant amount of input, you should see it at the top instead. So table 4 is input, table 5 is output, where we've got this unknown file, where in this case, it is actually standard output that is being read in from all the tasks collected by Slurm and aggregated and presented to the standard output of my terminal session, because I ran interactively. And then we've got more stuff from the ROCm Code Object Manager, which is pretty minor, but shows up because we aren't doing much. So that's the end of that file. What if we want more stuff than that? For what we can do, well, when we run Perftools Lite GPU, it generates that default report at runtime, but it also saves data. And it saves data to a directory of the form, the executable name, followed by some unique ID and a T. That's because Perftools Lite GPU is a tracing experiment. So the T means it's tracing. And when it generates that default report, it also generates the AP2 files that we will need for Apprentice 2 later. So what we can do once we've gotten this far is we can generate other reports using this directory's data using Pat report, and we can visualize performance with Apprentice 2. That's what we're going to do. First, let's look at Pat report, which gives us some useful things that weren't in the default report. In particular, I like this report accelerator time, because it gives us important information like this column, the significant data copies, which because Faces really tries to use the GPUs as much as possible, there isn't much data copied in and out. But if you're porting a real application, you'll probably be somewhere in between, where there are phases where you do need to copy data in and out. And this will show you where that's happening. And then we see the kernel launches, but this time they are in order of accelerator runtime, which is what I would usually care about to figure out what kernels I need to look at. So here are some additional options I like to add to the report to give me some line numbers and locations in the code, like the files. But so I am getting a line number, I am getting a file path, and I am getting the function, but this isn't exactly what I want. And here's the issue. In C++, codes often launch kernels from template functions that take lambda arguments. That's what I did with Faces, and that's the case where the real kernel code is in the lambdas. And so that's what I really want to see. So this is common with portability layers. So Faces has a very lightweight portability layer that is specific to it in that header gpu.hpp. But this is used commonly with things like Cocos, Raja, Alpaca, Yakul. Those are just a few of the portability layers you might use. And the templates in the portability layers get inlined into your user code. So when you get to the profile, it shows some line numbers somewhere down deep in the portability layers, instead of the line numbers where you actually have your lambdas defined. So for example, here's a call to the Faces share method, and it tells me where the share method is called in the main program. But instead of telling me where in the share method I'm creating my lambdas and calling the portability layer, it gives me lines down inside the portability layer. So share is a big method with lots of kernel launches, and so I can't really tell where these are in the code that I wrote. So a workaround is to turn off compiler inlining of the top layer of the portability layer templates. So GPU4 is my portability layer function, and I just add this if def craypad is only defined if I'm using Perftools. And by not inlining that, I should get better information, and this should not have a significant impact on runtime. You don't want to stop inlining of templates in general, but by stopping this top layer, there's definitely going to be a kernel launch in there, because that's what this layer does. And a kernel launch is going to take a lot more time than an additional function call on the host. The problem is that this requires changes in whatever your portability layer is, this if def and not in your user code. But when we do that, which I did here, I changed the code, recompiled, reran, and then regenerated the report. I got the actual lines in the share method where the lambdas were defined that take the most time. And interestingly, this here we have where one call became two, where it did just show one line for GPU run 3 by 1, and now we're seeing 2 lines for the 2 separate calls to that. Yeah, I think Steve answered the question about the reordering. It's for Cray MPI, not the Cray compiler. So that's my favorite pet report when I'm doing things with AMD GPUs. Let's dive into Apprentice 2, which is our visualization tool. So first, you can download the Apprentice 2 visual part to your local computer, and you find it by logging into the computer that you're going to run Perftools on. And at this location, CrayPat root share desktop installers, there's a couple of these installers where I'm using a MacBook, so I download DMG. There's also a .exe for Windows. So download that to my local computer and install it. And I can run it locally, so I don't need, so in this case, I don't need a VNC like Steve had to use for the stat tools. And from my local computer, I can open a remote data directory. So I enter the computer I care about, the password, and navigate to the remote experiment directories, which are again, so this is on the remote computer, it's the executable and some unique ID T. So I pick one of those and I get this display. Now, let me first say that it has excellent help information. You can get the documentation locally by going and clicking on the help panel help, and up pops this PDF. It's less than 30 pages, but chock full of great information for details on how to use the tool. So here's that main screen again. If you're like me, the first thing you want to do is be able to see it better, and so you can increase the font size, which I did here. And then one thing to note is this text balloon with a bright orange text balloon with an I in it, and that's an information balloon. And so you can hover over that, and this is the way it gives us those observations. So we saw this observation earlier in the default report, talking about how we could potentially improve our performance by rearranging our ranks. Also, if you see a report that's particularly interesting to you, like this profile that's averaged over all the processes, you can get a text copy by right-clicking and then left-clicking and copy data, and that's the text that was copied with the CPU and GPU information. So now let's first look at the pie charts of the profiles. You can either click the big one or the little one over here. And here we see a sort by calls and sort by time. I typically use the sort by time on the right. This isn't the only way we can view these data. There's this little arrow button in the top right that if we click that, we can switch to a bar chart. And so here we have the time and the number of calls ordered by the time it takes, averaged over all the processes. We can also get a sortable table by clicking the button again. Yeah, Steve, maybe you know the answer to that. I don't know if there's a Linux client for Apprentice 2. So here's the table where you can click on these you can click on different headings to get them sorted in different orders. And then if we click one more time, that was all of them. We're back to our pie chart, which is probably my favorite of these views. Then on the pie chart, we can open a load balance report for any particular function by clicking on it. So here, let's look at hipstream synchronize, which takes a whole lot of time. And we get this report where we see indeed there's one process that's taking significantly longer than the rest, where you also see these lines where this is the minimum, this is the average, and this is the maximum. So here they're ordered by the average time. You can click on the PE column to order by PEs to see if there's a particular pattern. So now let's shift to the text report, which, I mean, it's kind of boring to use Apprentice for this, but one thing you can do from here is if you have it loaded up, so this is that default report, you can in fact change to a different report by right-clicking and then left-clicking on custom options to generate the other report. And so here I've used that ACC time report and the options to show line numbers. And we get the report that I generated earlier with Pat report, but I can do it right here on my laptop. So next, let's look at the activity graph. So here we have the activity over the range of MPI tasks. And we can dive into one here. Let me go back. So here's an outlier. It's acting funny. Let's dive in and get the details. If you hover on the task, you can get explicit numbers. And it has this radio button in the top right, where here we're looking at activity over PEs, processing elements, which is the same as MPI tasks or MPI ranks. If you hover over the time, it tells you I can't do that. You need to rerun this code with what we call non-summarized tracing. So this is the default run is a tracing experiment, but it doesn't save all the data from the trace. It summarizes it as it runs. And we have to run differently to get the full trace. And I'll talk about that in a couple of minutes. Next, let's look at the IO table. So here we have a sortable table where, again, if you click on the various columns, it can order it differently. Next, let's go to the call tree graph. So this is kind of difficult to read right when you first open it. So I do a few things to make it more legible. First, I hide the function profile that's on the left, and then I zoom out to see the whole graph. And so here we have the whole function profile for call tree profile visualized. So boxes that are wide means you're spending a lot of time in functions that are called by this function. So we see that with the whole program, which calls everything. Whereas things that are tall means that you spend a lot of time within that function. And then within that tall box, the light purple is the minimum across all the processors. The darker purple is the average across them. And then going all the way up to yellow is the maximum time across all the processes. So it's a quick way to see where there's load imbalance, where in your call tree you're spending the most time, et cetera. Again, if you hover over the bright orange text balloon, it gives you some information and observation. So it's saying that there was a lot of load imbalance in the hipstream synchronize function for this code. Next, let's go to the MPI mosaic. So here we have a chart of the average time spent doing send operations from each source processor or each source MPI task to each destination MPI task. If you want to see the whole thing, you can zoom out so you can see the full pattern. You can also, instead of viewing the average time, you can look at how your communication is structured in terms of the total bytes transferred. And so you can see there what your communication pattern is among all the processes. Also, instead of doing it by task, you can do it by node. So when you first do that, and if you zoomed out, it's going to shrink down to something about 1/8 the size. and then you can zoom it back out to get a good view. And see here, for example, that we're doing most of our communication on node already. So that's pretty good. Now there's this compare menu option. What does that do? Let's look at that. So here I'm going to compare a couple of runs. I'm running faces with a 1D decomposition and a 3D decomposition. So it's the same amount of work, the same number of spectral elements, but in one case they're in 3D blocks, in another case it's a 1D decomposition, so it's skinny slabs. After I've run them, I open the directory of data for the 3D run, then I open it for the 1D run, and I click the compare merge for comparison, which merges the two that I've already opened. And I get this kind of display where it's comparing the 1D on the left with the 3D on the right. And I see that the 1D has both longer time in MPI wait and a longer time in the accelerators. So it's using the accelerators less efficiently as well. We can see part of the issue by looking at the MPI mosaic. And here, the difference in the decomposition is pretty obvious. Where the 1D, it's only to a neighbor. So I've used this to compare decompositions. If you could use a comparison also if you're doing a code change that you think might make the code faster, and compare the two runs and view them side by side. So now let's look at doing a full trace, which you do by setting this pat RT summary environment variable to 0. So recall from the previous slide that Apprentice 2 told us to rerun the code with non-summarized tracing. And the way we do that is to turn off summarized tracing. So you set this environment variable and you run again and open it up in Apprentice, and you get some new options at the top. You also get these calipers at the bottom for you to set what time range you're going to try. In my experience, there are better ways to set the region that you want to look at, and I'll describe that in a minute. I tend to not mess with the calipers. I use other avenues within Apprentice 2. So let's look at the timeline. This is our first view, and it doesn't look like there's much there, but let me show you how to tease the information out of this. First, let's see more of the call stack by dragging down that bar so we can now see it's a little bit deeper. Then I'm going to switch the histogram over to kernel execution time. Click. And then let me describe. So we got the calipers at the bottom, but we got these two things. One is called zoom and one is called magnify. And let me describe how I like to use these various devices. First, by clicking in this time bar, it moves where you are in the upper window. So if you see the little red line where it is now, in the kernel time, it's kind of in an empty space. And I'm going to click just to the right where the kernel histogram is showing some stuff going on. So this red line is, there's nothing here. So we're going to move it over here where there's stuff. So here we have some stuff. And so just to emphasize, clicking down here changes what you see up in this part. So you could click in like over here to see what's going on in these, or over here to see what's going on here. Now, once you've located yourself down here, you use the magnify to zoom what's going on up here. So let's zoom in. So now the top part is zoomed in, and I like to do all the zooming and moving around up here and leave this part as the full timeline so that I can navigate more easily. At the top of this zoomed in area is the host call stack. So the top line represents main, and then the farther down you go, the deeper your call stack is going. So each line is a different layer of the call stack, a new function call. Down here, the separation is different. These are effectively streams. And so we're looking at accelerator kernels. And so we are getting, by these being two different streams, you can see they're overlapping. So we are getting some overlapped execution on the device. You can hover over, so if I hover over one of those gray bars, it turns pinkish purple, and I get some details like what the function is and how long it ran. And if you hover above in the call stack, it'll tell you what function that is. And in particular, the reds are places where MPI is waiting. I think there's discussion in the chat about using Linux. So this timeline is all for the default task PE0. To see a different PE, you can enter a different number in this little text box. And so, for example, here we are switched to PE31. And so you really are only looking at one at a time, but that can be useful when you're trying to figure out how things are overlapping, in particular, how MPI and GPU execution are overlapping on a particular processor. So next, let's look at this traffic display. And I just want to warn you that you really only want to do this if you have a short run with very few MPI tasks, because otherwise your computer is going to be taking a long time to generate the display. And Faces does a lot of small communication. It's mostly a communication benchmark. And so, you know, after like a few minutes, this is what I got. I didn't dive into it too much because I wasn't really debugging how the MPI communication was going on. But if you get weird communication difficulties in MPI, this will dive into the very gory details of exactly what messages are sent where to every single process. And so at 64 processes, that's really too many for me to use effectively. It needs to be something smaller to take advantage of this. So I don't use this much. So let's go to somewhere that's easier to deal with, the moving on to plots. This is a timeline like we had before, but instead of kernel execution, this compares MPI and IO. So this is more for traditional, you know, CPU-based execution. And let's switch to the activity graph, which is a good way of summarizing things across all the processes. So when we were looking at the timeline before, that was a timeline for a single task. This is an attempt to give you information about the full timeline for all the tasks. And here we're seeing activity over time. So the bottom is the time now. And here is a percentage of the MPI tasks that are in each state, where that state can be MPI synchronization or waiting for a HIP call or so on. So this is host centric, but it does give you some idea of the different things that each of the tasks are doing. Now let's look at the overhead that comes from using these tools. So first, in terms of size, the original executable was less than 1 megabyte, and the instrumented one was 2 megabytes. So that's not, these aren't big numbers, so that's not too bad. When I did the summary run, the data output directory was 35 megs, not bad at all. But when I did full tracing, it jumped up to 12 gigabytes. So that's where we're getting big. So Faces has internal timers. It's a micro benchmark. And so this is how the internal timers compare. So by doing standard Perftools like GPU, which does the summary run, it increases the measured sort of figure of merit just a little bit. By doing full tracing, it increased significantly to about double. But where we really take a hit is on elapsed runtime. So this is the total runtime of the job, where the original took, 5 or 6 seconds. By turning on the profiling, after the run, it generated the profile report on the fly as part of our job. And so it took about 20 seconds. And then Without summaries, it took significantly longer because it's basically storing everything. Now, a caveat, this is stored in an NFS home directory, so your mileage will vary, and in particular, you can get better performance once we have a high performance file system that's available, but you do need to watch out for how much longer this will take and how much space it will take. And in particular, this is all happening during the runtime of the job. So at the end of the run of the application, Perftools is going to generate a report, and it's going to be holding all the processes of that job for all that extra time. So that can be a significant cost when your overall cost, particularly to your allocation, when you're using a large fraction of the machine. So let's look at a way around that, and that is to use pat build instead of Perftools Lite GPU. So the changes to use pat build for ProgEnv AMD are that you do a module load Perftools instead of Perftools Lite GPU. And then after your build, you do not have an instrumented executable. You need to instrument the executable explicitly. So there's this pat build command, and the -w says to do a tracing experiment and trace each of the user processes. And the -g says we also want to trace HIP calls, IO, and MPI. So this is a good approximation for what Perftools Lite GPU gives you, but done after the fact instead of as part of the build. The -f just allows me to do multiple builds where it's going to overwrite the existing executable. Another difference is with ProgEnv, with Perftools Lite GPU, when it instruments your executable, it saves the original executable as executable plus a rig, and renamed, or the instrumented executable is the original name of your executable. But with pat build, it keeps the original executable named as before. So in this case, faces, and after instrumentation, it creates a new one that will be faces plus PAT. And then to run it, the changes that we need are to change the module load, Perftools instead of Perftools Lite GPU. And because the name of our executable changed when we instrumented it, we need a plus pat. Then when we run it, instead of getting that big report, we get minimal extra output just saying, I wrote data to this directory. And that's all it adds. Here's how to do it with HipCC instead. We change the module. Again, we need to use pat ops, but here we just drop the light argument. So instead of include HipCC GPU, we just don't add it. And then after the build, we have to explicitly, again, instrument the executable. Then to run, just a different module, add the plus pat, and with limited extra output. So here, let's compare overheads. So this is the elapsed runtime. So if we compare the Perftools Lite GPU with the one with the pat build version, because it's not generating a report at the end, it's just a little bit longer than what we did before. And we can even do a full tracing experiment in just a little bit more time than we were doing with a summary experiment that also generated the report. So we're getting significantly lower overhead by deferring the generation of the report. But that means we need to generate a report. And if you don't do that and immediately try to use Apprentice 2, you'll probably get a complaint that says the directory contains no AP2 files. And that's because you need to run a pat report to generate the AP2 files. That happened automatically with Perftools Lite GPU because it did a report. So do a pat report first, then you can use Apprentice 2. Any pat report will do, including just the default one with no extra arguments. But if you do a really big run, or if you are generating a pat report and change your mind about what report you are generating, and you Control-C out of your pat report, this could cause you to have incomplete AP2 files, so that when you try to view it with Apprentice 2, it will give you incomplete data, won't really tell you a good picture of what's going on. And running pat report again, pat report will just say, hey, I see some AP2 files. I don't need to regenerate them. So to get it to properly generate the AP2 files, you need to remove all the old ones and run it again and let it run to completion. So here are my takeaways for using Perftools. You can build with either Prog and AMD to use the Cray compiler wrappers or HipCC. This is in particular, this is specifically for HIP code. Then you instrument with, this is my favorite for AMD GPUs, this pat build, which gives us relevant information in a tracing experiment. By using pat build instead of Perftools Lite, you run with minimal overhead, and then you generate reports. Either the default report or the one I like is the one that has accelerator time with the line numbers and the locations in the file and the function names. If this, so this is all useful for your initial profile. If you need to really dive in and get full tracing, you don't have to rebuild. You just rerun with an environment variable set to 0. Make sure to use pat report to generate your AP2 files before trying to use Apprentice 2. And you can use Apprentice 2 to explore load imbalance and MPI accelerator overlap. That's what I like to use it for in diving into the traces. So that was Perftools. I don't think there are outstanding questions about that in the chat. So I'll go on to Rocprof and what it can be useful for. First, building for Rocprof, well, you don't have to do anything, and it works with both Prog and the AMD or HipCC. But it gets a little tricky when we decide to run it. Rocprof wasn't really designed for multiple tasks. And so by default, each MPI task writes its own trace output file. So we have to do something to deal with that. Otherwise, they'll just stomp on each other writing to the same file. So one way to do that is to kind of inline a wrapper script by using bash-c as the command you're going to run, and then give it the total command to run within the wrapper. Then you use Slurm environment variables to name each file differently for each MPI task. So here I've named the files Slurm job ID dash Slurm proc ID. So the proc ID will make sure that each MPI task gets a unique file name. These single quotes are critical because I want to make sure that these environment variables get expanded when it actually runs inside the srun, not when this srun command gets run in this shell. Then the rock profiling happens by calling rocprof with the hip trace argument, and that traces hip calls and kernels. But what we get is a whole lot. So at runtime, this generates over 1 million extra lines of output. It also generates 6 separate files per MPI task for a total of 384 files and 6.3 gigabytes of output. So I just generated tracing for each and every one of my MPI tasks. Often when I'm doing a full tracing experiment, I want just one or a few MPI tasks of tracing. And so we can revise our inline wrapper to do just that. So here we pick a task ID. So instead of everybody doing rocprof, just one task does it. Here I pick the root task, but it could be, anything between 0 and 63 in this case. And we get less extra lines of output. We get 6 output files and only 100 megabytes. So that's not too bad. And so here's a comparison of the elapsed runtime that we have to deal with. So by doing one file, it takes significantly longer than the initial run, but by generating all 64, we really hammer the file system and double it beyond that. So here I just ran it on a single process, and that single process gives 6 additional files. Where the CSV files, that CSV means they're comma separated values. So I'm going to look at the stats file. So here's results.stats.csv. So typically a CSV file you can load into something like Excel to view it. But unfortunately, at least in this version of ROCm, it also puts in the function without quotes around it. And so the commas that are in the function call confuse the CSV interpreter that would be in, for example, Excel. And so it's hard to use there, but you can just look at it with the raw file here. And for example, see that the last column is the percentage of runtime of the GPU kernels running. This is the percentage of the time spent in that kernel, and they're ordered by that percentage. And so you can see that GPU run 4x1 took a 70% of the time. So here's a quick and easy profile. It's kind of tricky to read, but it's because it's not too big, it's just a line for each of the kernels that you call. Aggregated over all those calls, it's not too hard. The really cool stuff comes from the JSON file, which is a trace file that we can view with Chrome, the Chrome web browser. So let's look at some Chrome tracing now. So to get to Chrome tracing, you open Chrome. So this is on my laptop, and you enter the URL chrome://tracing, and that gives this screen, and I can load my JSON file. So the first thing I did was SCP the JSON file from Pressure to my laptop, and then I load it locally on the laptop. And then I get this display. So let's dive into what's going on here. First, I'm going to drag down the info pane so that we can see stuff. And one interesting thing is we get a whole lot of lines for different accelerator stream objects. So one difference between Rocprof tracing, at least this version, and what we saw with Apprentice is that, well, let me step back and say Faces does multiple iterations where it creates a couple of streams to run, destroys those streams, creates new ones, and does it again. And Rocprof records each of those as, or at least most of them, as separate entities. And so we get these different lines as the run goes across, whereas Apprentice 2 appeared to just keep the total alive at any one time and to reuse that. So because only 2 streams were used at a time, it only had 2 lines instead of, in here. The default navigation tool with Chrome is the Zoom tool, and that's the one, I think it's a good default because that's the one I want to use first. It's a little tricky to use, but very effective once you get used to it. You click and drag upwards to zoom or downwards to zoom out, and the zoom occurs left, right, centered on where you're clicking. So by clicking here and dragging up, it's going to push this side this way and this side that way. So if you get it a little off, you can just move on your screen and zoom there as a new centered piece. So if I click on this far left side and zoom, it's all going to push right. If I click way over here and zoom, it's all going to push left. And I do in the middle, it goes both ways. So let's zoom in a little. So here we've zoomed in some. We're in that first part. Now we're going to zoom in again to get some real details. And here I'm down to where I can see individual kernel launches, individual HIP calls. And I hope you can see, I can see it on my display. There are these little red lines that connect so I can see which HIP launch goes with which kernel. So now I'm going to drag this bar back up to see the info pane, and then double click on one of the kernel launch bars and get more detailed information about what was launched, how long it took, and more about the arguments and dependencies. So some takeaways from using Rocprof. You can run Rocprof. Well, first, I recommend running Rocprof on a small number of your MPI tasks because it's going to create a lot of files. You don't have to recompile. You can get a quick profile of your kernels from that stat CSV file. And you can view your traces with Chrome. And you can use that to see where the host and accelerator are waiting for each other, see overlap among the kernels. But the one thing that's missing from this view, I like how it connects the HIP calls with the kernels, but you don't see MPI. So that's one of the advantages of viewing tracing in Apprentice 2 is you can see the interaction between MPI and the kernels. So now let's dive into compile time performance measurement, where we're actually going to be looking at some assembly code, or at least some assembly files. So first, I'm going to pose a question that has a lot of details of the architecture, and those details are all public and available in this document. You can see where the document is online. So I've got this simple word problem based on the MI250X GPU. So try to keep all this in mind as we think through this problem. So each wavefront of this GPU has 64 threads. So that's like a wavefront of 64 threads. Each work group that we launch, each also called thread blocks, can use between 1 and 1024 threads. So variable size. Each compute unit on this GPU has 4 execution units, EUs. They're also known as SIMD units. So there's 4 of those per CU. And all the wavefronts of a work group have to go on the same CU. So whether it's 1 or 1,000 threads, they all have to fit. When that work group is launched, all its wavefronts have to execute on the same CU. And they can execute across different EUs within that CU. But each EU, execution unit, can have up to 8 active wavefronts that it can choose from when it decides to run its next instruction. And the number of active wavefronts that an EU actually has is what we typically mean by its occupancy. So full occupancy would be if every execution unit had 8 wavefronts waiting to run, and less than 8 means some smaller fraction, some lower occupancy. So it can run up to 8. It can have 8 active wavefronts where it runs one at a time, pipeline though. But also each EU has a limit of 512 vector registers. So each vector register stores a wavefront worth. Each register has stores 64 32-bit values. So we've got 512 of those registers that it can use across all the 8 active wavefronts that it has, that it can possibly have. So based on all this, I'm going to ask the question, how did Odysseus navigate the Strait of Messina? Now, I realize there may be some of you for which this question does not have an obvious answer. And so I thought I should dive in and explain how these are connected. So first, I'm going to talk about the Scylla and Charybdis of accelerator kernels, where here Scylla represents low occupancy. So if you use too many registers, you limit the number of wavefronts that can be active at any given time. And so that occupancy is devoured. The accelerator resources are devoured by Scylla. So Charybdis is, in this case, spilling registers. So by limiting the register use of a kernel, you can increase the number of wavefronts that can be active at any given time, but you're going to force the compiler to spill registers. And that means that every thread is going to store and then load registers to and from memory. So spilling registers on a host processor might not be such a bad thing. There's a big cache. There aren't very many registers. But on a GPU, it can be a significant cost because there's a large volume of registers. And so that can suck down your memory bandwidth. So a way to navigate this, adjust for it, is the launch bounds annotation that can go on a kernel launch. So launch bounds takes 2 arguments, where I've listed them as Tmax and Wmin. The Tmax argument, the first argument, is the upper bound on the number of threads per work group that you're going to call this kernel with. So it defaults to the maximum 1024 so that you can call it with any number of threads per work group. If you know that you're only going to call it with some smaller number, you can set tmax smaller. But if you try to call the kernel with some value larger than tmax, I think it fails at runtime now. So you can set this value lower to let the kernels have access to more registers. That way you can avoid spills, but you may reduce your total occupancy. The second argument that I'm calling WMin here is the lower bound on the wavefronts per execution unit, where the default is 1. So the compiler is allowed to use so many registers that only one wavefront can be active for this kernel at a time. It's going to try and use as few registers as it can so that it gets the maximum occupancy, but you can force its hand by setting a higher limit. And then it will guarantee that that number of wavefronts will be able to be active in a given EU at a given time. And so this can improve occupancy, but you're likely to force the compiler to insert register spills. So we've been using faces. In this case, I'm going to switch to a different benchmark, our HIP implementation of Quicksilver, because faces has very small kernels that aren't good for illustrating this, whereas the Quicksilver benchmark has one very large kernel. So the first thing to do to figure out what's going on is to add the save temps argument to your compile line. And that's going to add a bunch of files for each file that you compile with save temps. So here, this is just for main.cc file. I get a bunch of extra files, but what I really care about is the one that ends in my GPU architecture.s. So GFX90A for the MI250X's .s. And then I'm just going to look at it with less. So we're going to see a few less screens. So here we've dived into the file. The first thing we're going to do is search for the kernel that we're interested in. And for this, the kernel name happens to be cycle tracking guts. So we're going to go there. And then once we've gone to that part of the file, we search for specific information, kernel info. That doesn't depend on the name of the kernel. That's the comment that we're looking for within the assembly. And so here we have the kernel info section. And within that, there are two particular lines that I'm interested in. One is num VGBRs for waves per EU. So that's the number of vector registers that this kernel is going to use. And in this case, it's 110 vector registers. Each EU has 512, so we can figure out what the occupancy is going to be from there. 512 divided by 110 gives 4.65, which means it could have up to 4 wavefronts active at a time. And sure enough, when we look at occupancy, the occupancy is 4. If you do the reverse computation, it says that for an occupancy of 4, that means you had to use 128 vector registers or fewer. So these numbers are consistent. There's one more thing I care about, and that is the spill count. So I search for that. And what I particularly care about is the number of vector register spills. So there are SGPRs, so the scalar registers. So that's not great to spill, but it's not, in my experience, it's not as big a deal. You definitely want to avoid spilling vector registers, and here we are not. So that's great. So instead of lessing through a file and searching for particular things, you can cut to the chase with this particular grep command, where I search for capital GPR, lowercase s, occupancy and spill count, and get those numbers directly. Now, let's say I've heard high occupancy is good, so let's crank it up. So we're going to add a launch bounds that sets the occupancy up to its maximum value of 8, unless it doesn't go to 11, just 8. and then recompile. And we were successful in that we got our occupancy up to 8. And because we have an occupancy of 8, each kernel gets 64, each wavefront gets 64 vector registers. But as a result, we now have a significant set of vector spills. So here are the results. This is performance. So longer is better, comparing the original case where we didn't have any vector spills with double the occupancy. And what we see in this case is the occupancy is less of a help than the spills are a hindrance. And so, and I often see that this is the case, that it's better to avoid vector register spills than to increase your occupancy. But that raises the question of why do we have these two awful choices? Can we do something better? Can we reduce register pressure so that we push these two monsters apart and have smooth sailing in between? And I have a couple of examples of how to do that. One is to avoid assert and printf inside your kernels because they use a lot of vector registers. And in particular, abort, unlike assert, is cheap. And so it is safe from a performance point of view to do if statements followed by an abort. Another trick is to wait for compiler improvement. So instead of being low-hanging fruit, you just wait for the fruit tree to grow. This is actually effective in the sense that ROCm keeps getting better and better at optimizing its use of vector registers. But of course, it's not a very effective way to improve your code immediately. One strategy that I've seen to be effective, in particular, it was useful in Quicksilver, is to avoid arrays on the stack in device code. And I'll talk more about that in a minute. And we are actively looking for more good strategies for reducing register pressure. So here's an example of what I mean by avoiding arrays on the stack. The pattern you look for is some small set of constant size arrays. Often 3 is a common number for the number of physical dimensions. 4 is also common, where there are small loops that set the values and then small loops that use them, and they're separate. So this is actually very reasonable code to have on the host. It often vectorizes well, uses the vector instructions on CPUs, but it absolutely gobbles up vector registers. And so one thing to do is to try to fuse all these small loops. And that way we can move these vector temporaries, or pardon me, array temporaries inside the loop. They become scalars, and our use of vector registers can decrease by 3, 4, or more, depending on the size of n, and it reduces our vector use and gives us higher occupancy without vector spills. So some takeaways from this section. If you know the maximum workgroup size that you're going to call a kernel with, it's good and safe to put a launch bounds with that number on it. But you probably don't want to use the second argument of launch bounds to force a higher occupancy because it's probably going to give you register spills. You can use the save temps argument when you compile to get annotated assembly code. And you can search that with this grep statement to figure out what's going on with your register use, your occupancy, and spills. And you want to look out for low occupancy and for non-zero vector spills. And in that case, you want to try to reduce your register pressure in your code, which, you know, we're still looking for good techniques for doing that. So we're about getting close to the end here. Oh, Tim has another good example. Transcendental functions or similar math functions can cause register use. And he gives the explicit example of if you've got a pal to the second power, it would be a lot faster and lower on register use to change it to a multiply. So here are some topics that we'd like to talk about sometime in the future, but I can't make any promises right now. First, more coverage. So we have a little bit of coverage from Steve on OpenMP offload. We'd like to dive in more there about how to do both profiling and even conversion of your code of an existing OpenMP host code to offload. Didn't talk any about hardware performance counters, but some interesting things are likely to be available there. It would be great if we could talk about in-kernel profiling. So the profiling we have now is good at telling you which kernels take the most time, but we're not yet telling you which lines within the kernels are taking that time. Also, love to talk about compiler reports that give you good information and how to generate roofline plots. And in particular, the thing I would really like to talk about in the future is performance tuning success stories, where we use these tools and whatever best practice techniques we can find and have concrete stories of how they improved the performance of real codes. And we hope to generate those in the near future. For more information on these various topics, there's a good place to start on the computer is man Perftools to look at all the different kinds of PAT reports there are -O-H. Also, support.hpe.com is the closest thing to Cray, pubs.cray.com we have now, and a search for performance analysis tools should give you some useful things near the top of that search. Also, information on some of the tools that I use both from ROCm and Google Chrome. This is also an acknowledgement. Thank you to these vendors for providing these tools. I like to use them. And here are various links to ROCm documentation, and Rocprof --help gives you more information if you're on the machine. So that's all I have. I don't know if anyone has any additional questions.
Yeah, hi, this is Kevin Huck. I have some questions. Thanks for this. This is a great presentation. I appreciate it. One question about the avoiding arrays on the stack. That seems like something that the compilers could certainly help with for small array sizes. Is there, or at least constant array sizes? Is that something the compiler team is looking into, as opposed to having everyone update all their kernels?
So I'm not sure how, I'm trying to figure out how a compiler could avoid the use of the registers when they are, I guess if it did kind of.
Well, I'm just thinking we have some kernels, for example, that have, it'll just say, you know, something array size 3 because it's XYZ.
Right.
And so, I mean, it's a constant size. Couldn't that just be expanded by the compiler to three scalars?
Well, 3 scalars would still be using 3 vector registers. And so the trick is going from the array of 3 to a single scalar. So I guess, so theoretically a compiler would need to fuse those loops, see that it's a temporary array that it can replace with a single scalar. Do you see the complexity that it has to deal with? So so it may be the case that after it has gone to, closer to, but maybe like at LLVM level intermediate format, it could see, it could expand the array into separate scalars and then do the scalar analysis to see that these are all, that it could do register reuse among them in a cleaner way. It's already doing really aggressive reuse of the registers. But I mean, the issue basically comes down to in your code on the host, you really are using them as 3 separate scalars. And probably the way the code is written, it may be very hard to tease apart that they actually aren't dependent on each other or can be used to accumulate. Like if you have a place in your code that adds them to a single value, it would be a change of kind of what your code means to add them individually instead of on a single line. So that's a common thing. Like if you're computing a distance, you would just, use all the values of the array explicitly in a single line of code, right? You'd square them and take the square root. And so you would need to conceptually change that so that you're accumulating the squares and then separately write a square root line if you want to use it with a single scalar within a loop. Did that make sense?
Yeah, I guess I was just misunderstanding what the optimization was. I thought maybe it was just the array indexing that was consuming vector registers, but
it's literally the values.
Okay.
So by using
I understand
by using an array of 4, you just consume 4 vector registers, and where it could be 1 if it's a single scalar. But that's basically the example is you're trying to replace multiple vector registers with 1 by reusing it, and so you're changing the order of code to do that. And this is one of those portability issues also, because those short vectors of explicit size are probably really good for things like AVX, where it can just, a compiler, it can find it very easy to change those to vector instructions. And yet inside a kernel, they can consume a lot of registers.
Thanks. And I had one other quick comment. The most recent AMD compiler, the 510 compiler, has the OpenMP tools support built into it. So for OpenMP target offload, there's some events that your tools could be capturing from the runtime. As far as I know, it's only from the AMD compiler so far. I haven't tested with others yet.
Yeah,
well,
and so
go ahead, Steve.
Let me address that. Yeah, so we do have some OMPT hooks in I don't know. I think, yeah, Perftools does capture some OMPT hooks, and I think we should have that in our compiler as. I don't know the state of our OMPT implementation. I'd have to check on that. But we can capture that, and we also do support. I know GDB for HPC and rocgdb have OMPD hooks and things and support as well.
Excellent, great, thanks.
Yeah, I know the intent for the Cray compiler OpenMP is full support for both the profiling and debugging interfaces.
Yeah,
if it's not there already.
Yeah, we can add that to the list of future things that I'd like to look into and try and do a talk on is some of the OMPT and OMPD stuff. So while we have this page up, I just want to point out, so, I mean, we've been answering questions in the chat. I think I answered one on the event page as well, but our emails are here, and please do feel free to reach out for us. I mean, we are the Frontier and or El Capitan Centers of Excellence, right? So we really are here to make sure that you succeed on these machines. So please don't be shy about reaching out if you have questions about this or anything else, really.
Yeah, and I want to add, coming up, the first one will be next week. We're going to have office hours for Crusher users that you can sign up for. And I wish I had the link in front of me, but so OLCF it has started a sign up system for these office hours. We'll have one next week and then for the next few weeks, and I think it'll be a rolling sign up. So look for Crusher office hours for ECP users where you can talk one-on-one with us. If you hit issues on Crusher, I encourage you to send an email to help@olcf.orlnl.gov, the help email, because we're going to be able to start seeing the issues that Oak Ridge thinks we can help with. So we'll be better integrated with that. So that's not necessarily a separate thing anymore, in the sense that if you send in a ticket, we will be able to see it and act on it. Thanks, Tom. Tom put the links in the chat. Great. Well, if there's no more questions, it's been a pleasure talking to you today. Thanks, Steve, and thanks, Kostas, for helping us out with the material and answering questions. And Tim, I noticed that Tim Maddox, who is also a member of the Frontier COE, answered some questions. And I look forward to talking to you again sometime in the future.